Okay, I'll get going in a second. If you want a chocolate bar, you've got 30 seconds to grab one. You get in a break too. So,
Anyone.
okay, so let's get going. So, Hale, are we live? Is it all good? Okay, great. Okay, so today we talked about logic block architecture last week. Today we are going to talk about other blocks that you have on an FPGA. Okay, a little bit of administration first. So assignment 2 is due tonight. I assume everyone here are the people who got their assignment done lots of time. Those who are still working on it may not be here. How'd it go? People like in good shape, or they're counting on a final 4 hours of like high productivity? Okay, you're 2 years overdue already. So, okay, so assignment 3, I'm going to release either tonight or tomorrow. It's going to be due November 26th, so 3 weeks from tomorrow. It's worth 22% of your final mark. And it's a little different. You're going to develop a RAM mapping CAD tool. So this will all be in the assignment, but I'll give you a quick overview. So this is basically you're making a tool that can take the RAMs that a person wants in their design and map them to the physical RAM resources on a chip. So that is called RAM mapping. So it's a form of technology mapping. It's basically a more complex form of bin packing, and bin packing is a computationally hard problem. So generally to get a perfect solution, there's only exponential time answers, so you're generally going to have to resort to heuristics that get hopefully reasonable solutions, and they're just kind of good ideas. If you're looking for literature for ideas, well, you can ask me for ideas, but if you go look for bin packing, you'll get some idea of what some of the heuristics for bin packing are. This is a more complex form of bin packing because you kind of these RAM blocks that you're packing things into on the chip, you essentially have a few different types, and they can handle a few different shapes of RAMs. So it is a form of bin packing, but with some extra constraints. This is a good advice for all engineering projects, but get something simple working first because this problem is reasonably open-ended. You don't want to go, I have an idea for the world's most complicated algorithm. I think 3 weeks sounds like forever. I'm just going to do the most complicated thing I can think of. There are a bunch of legality rules. You have to make sure you understand those. Get something working that passes a checker. So I'll give you a legality checker so you can see if you've interpreted all the constraints of what goes in a RAM properly. Make sure you can pass that checker. Then you can improve to reduce essentially the chip area. I'm going to give you I think 69 designs. Those designs are essentially pulled out the RAMs. Like all you care about is how much logic there is and what all the RAMs are. You don't care about anything else. So that's what I've given you so that it's relatively easy to parse. They are actually real designs. They're the ones that were used to architect Stratix 5. So I took them with permission, with that data with me from Altera. So I got that data from Altera. So it is real. And you're going to use them. The first thing you're going to do is write a RAM mapper that basically, given a target that's a lot like Stratix 4, like a real FPGA, you're going to see how well you can map to the RAMs on the chip. And the metric you're using is how big a chip you need, right? So we're essentially treating the chips as you can get a bigger or a smaller FPGA. You're trying to map the RAM so that you need as small an FPGA as you can. That's basically the first part of the assignment. And this is really the harder part, right? The software tool. You can write it in any language you want. There's no time constraint, like in terms of runtime. So as long as you can run it before the assignment is due, that's fine. You might get bored if it actually, there's no reason this should take a really long time to run, but I'm not going to check, right? So if it takes an hour to run, that's fine. But commonly you'll be able to run it in a few seconds. You're going to then take this tool that you've developed, you're going to use to explore different FPGA architectures. So in this first part, the architecture was fixed. We said it's just like Stratix 4. In the second part, you can change the architecture. What that means is when you're writing this first part, don't hard code everything. If you hard code all the RAM sizes, you're going to get that working, and then you're immediately going to go, I wish I didn't hard code all that stuff, because I have to go back and I have to change all these lines. So try to make it flexible. And what you're going to do in the second part is some exploration. You're going to try changing the physical RAM sizes and investigate essentially some trends, like what looks like a good set of physical RAMs to build in an FPGA to give you efficient mappings. Okay, and there's a prize. So if you get the best solution to part 1, which is the lowest area, you get an Amazon gift card. It will cover, let's see, I'm thinking of what fraction of your tuition it will cover. Okay, so depending on what kind of tuition you're paying, this could cover somewhere between 0.1%, perhaps up to 0.3%, if I didn't do a mistake there. So let's see. Yeah, I think that's about right. Okay, so probably not worth it if you're doing it for the money. You're doing it for the bragging rights. Okay. So you'll see the assignment, and I'll give you some more information next week if you have questions. Okay, so the reading that you hopefully completed over the 2 weeks that you had was the second half of the survey paper. If you're going to read, again, one thing probably in this whole course, you should read more than one thing, but this is probably a summary of much of the material about FPGA architecture. So it's probably the one thing you want to make sure you read. And hopefully you read the Stratix 2 paper, which introduced fracturable 6-LUTs. Okay, so for next week, so this week we're talking about function blocks. Hopefully we'll finish it. Maybe it'll drag into next week a bit. And then we're going to move on to routing architecture. So a couple of papers. First one is an academic paper that looked at basically how should we build routing switches, and concluded that we should build them in a somewhat different way that really limited our interconnect architecture but worked well. So it's a useful paper to read. We'll talk about it next week. And then this paper talks about everything in Altera's second most recent FPGA, Stratix 10. So it talks about how its routing architecture works some, but the main thing it talks about is the fact that they actually put pipeline registers not just in the logic blocks, but actually in the routing. Okay, so that was a pretty big change for Altera, and we'll go through a few recent architecture papers to see how have things evolved since this in both Altera and Xilinx architectures. But that's the bulk of this paper, is how do we put pipeline registers right in the interconnect, which is a pretty interesting idea. Okay, so where are we in terms of course concepts? So last week we talked about logic blocks, and today we're going to talk about essentially all the other blocks. And then next week we'll start talking about the routing that ties them together. Okay, so we're going to talk a bunch about on-chip memory architecture, and this is quite relevant to this next assignment. So next assignment should reinforce these concepts, so ask questions if any of them aren't clear. Okay, so memory architecture is quite important. So the number one thing that's on an FPGA was a lot of I/O, and then you have programmable logic with the programmable routing mixed in. That's like if you take away the I/O, which varies. For a small FPGA, you actually might have more than half your areas in the I/O. For a big FPGA, it might be 20%. If you talk about the core area of an FPGA, the logic and routing is the biggest thing, and then the second thing after that is the RAM. Okay, it's about 20% of the area of a typical FPGA is actually the RAM blocks, and that includes the routing that goes along with them. So we kind of always include the routing in these blocks. It has to satisfy a lot of different needs. So FIFOs are heavily used in FPGAs, and we talked earlier that if you're going to build a big FIFO, like quite a few words, and the words are reasonably wide, you could build that with shift registers, but generally building it out of block RAMs with read and write pointers that you store in registers is going to be more efficient and is going to take less power. So we use it a lot for FIFOs. What compute model loves FIFOs? So we wind up with FIFOs all over the place, but it's like, do you remember what compute model loves FIFOs? Yeah, so streaming with back pressure, right? Or you can call that an elastic pipeline. It has a few different names, but basically dynamic streaming architectures or elastic pipelines, they have FIFOs to basically buffer up data while you're waiting for the back pressure signal to go and tell something to halt. And we use that all over the place. If you have a DDR core, that's the way you interface to it too. You have FIFOs and you have back pressure. If you're using streaming hardware, you wind up with FIFOs and back pressure all over the place. So we need a lot of them. We use them to convert between clock domains as well. So if you talk to DDR, you talk to it at a very high speed, it dumps data into a FIFO at that high speed, and you take data out generally at a lower speed off the other side. So we can do clock domain crossing with a FIFO as well. So FIFO is a pretty important use case. Scratchpad RAM. So FPGA is used a lot for communications. So for storing packets, usually you'll try to store the packet body in DRAM because it's pretty big, but the packet headers you may store on chip. And you may store a few packets on chip if you're inspecting them and checking for nefarious content. So we use that for scratchpad RAM. Packets is a good example. Just constants. If you're doing signal processing, you've got all these constants for your filters or convolutions, for coefficients, etc. If you use soft processors or you use micro-coded state machines, so that's basically kind of like a soft process. Well, it's basically I've got control logic for some data path and it gets complicated enough. Instead of making a finite state machine, I might use a soft processor or I might use a micro-coded state machine, which is basically like similar to the control path of a processor with nothing else, right? You just have like instructions and branches that go back and forth. But I need a place to store all those programs, register files. So any kind of processor, I'm going to need register files, and that's going to be built out of RAMs. So lots of different things, and we do use them in all sorts of different ways. So they have to be reasonably configurable. So the first thing we should think about before we ever put anything new in an FPGA is, could we just build this out of the regular registers and logic? Right? These are highly programmable devices. Before we add any hard block that might or might not get used, we should just see if we can build it out of the stuff that's already there. So let's take a, well, so what do you think of this? Can I do this? Can I build memory out of registers and logic? What do you think? So Alex has an idea. What do you think?
Well, you said that RAMs are very plentiful in FPGAs that are built with them, so why can't I just use all of them for my RAMs? I think I might as well.
Oh, you mean the configuration RAM?
Oh, not just that, just like the actual RAM that are in like BLEs. You have RAMs that are also in like in the interconnect for some of these newer architectures. So we have lots.
So you're talking about using the registers?
Yeah, we have lots of registers to use there.
Okay, so yeah, so I can use the registers, right? My registers are memory, and I have logic, which allows me to build multiplexers and decoders, so I can build RAMs. So if I do that, there's a positive. You get exactly what you want, right? So if you need a RAM with 7 words and each word should be like 6 bits wide, you can build exactly that, okay? So that's good. If you need that to have 2 read ports and 2 write ports, you can build that too, okay? So you can build anything out of the registers and the logic that's on the FPGA, so we can build exactly what we want there. But the negative is that we have if you look at a basic logic element, you've got this whole lookup table, you've got all these routing ports to get in and out of it, and you've got a register. And you're basically just trying to use that register as 1 bit of storage. That's fine if you only need a few bits of storage, but if I need 4,000 bits of storage, I now need to use 4,000 basic logic elements approximately. Maybe each of them has 2 registers or 4 registers, but these are large numbers of logic elements to make a not very big RAM. Okay, so I'm wasting most of what's in my basic logic element just to get at that 1 or 2 or 4 registers that are in there. And I actually have to build a lot of muxing out of the soft logic, okay? And I have to use a lot of routing to connect all these things together. So, okay, so let's take an example. Let's say I want to build a RAM. It's not super big, so this is 8 kilobits, okay? So 256 words, so that's what we call the depth, and each word is 32 bits wide. Okay, so not an enormous RAM. And I want to build that out of the logic and the routing. So the first thing I need is 8,192 registers. Okay, so that's actually a lot of registers. If I have only a couple of registers per BLE, or let's say 1 per BLE, that's how many BLEs I need. I also need to decide, if I'm going to write a word, I need to figure out which word. Okay, so you give me an address. In this case, it's going to be a 8-bit address. Okay, so I need to build an 8 to 256 decoder, right? For every 8-bit value you can give me, I'm going to activate 1 row of registers. They're all going to capture the input data that I'm trying to write. Okay, so that's my write path. I need this decoder. On my read path, I basically have to build a 256 to 1 mux. Okay, so I'm going to send in a read address, and it's going to select one of these 256 words. So that's a 256 to 1 mux. How many of those do I need? Well, I need one for every bit in my output word. So I actually need to have 32 of those. Okay, so if you actually add up, what does this take? If we take Stratix 4, and this will be basically the same answer in ARIA 10, which you're using for your assignments, this takes 6,000 of their adaptive logic modules. So that's the fracturable 6-let. In Stratix 4, this had 2 registers and a fracturable 6-let. I need 6,000 of those. So that's a lot, right? Even a big FPGA might have like 1 million logic elements or ALMs. So this is a noticeable percentage of that. And a mid-sized FPGA might have 300,000. So I'm maybe using 2% of my design logic to build one not super huge big RAM. So I can do it, but I wouldn't want to do this for thousands of RAMs. And in fact, I couldn't. I'd actually run out of logic in the design. Okay, so it makes sense. So it'll work, but it's relatively big. Okay, so let's compare that to what if we built a RAM, right? We use like an ASIC technology. We build a hard RAM block, and you'll see how you build those in a few slides. But basically, Stratix 4 actually has M9K blocks. So it's a 9 kilobit RAM, and it can be up to 36 bits wide. So it can actually implement exactly this. It'll actually waste a few bits. So it basically can implement a 256 word RAM that's 36 bits wide. We don't need 36 bits, so we're just going to waste the last 4. But the area of this is equal to the area of 28 ALMs. Okay, so the reason I use Stratix 4 here is there's actually a publication that tells you how big the blocks are relative to each other, which for most FPGAs is not known. But for Stratix 4, we actually know. So it's 200 times more dense than building it out of the logic fabric. Even though in this case we wasted 10% of the bits. So even wasting a reasonable amount of this RAM, if things don't perfectly fit it, it's a huge gain. So we want to have RAM blocks, right? It's really not an option to not have these. Yeah?
In the prior slide, you figured that 20% of area is taken up by memory.
Yeah.
Is that using the RAM slices or not using the RAM slices?
Well, what I mean is physical area on the chip. So if I actually went and looked at the chip and I counted up how many of these, Stratix 4 actually has 2 kinds of RAM blocks. So it has these 9 kilobit ones. It also has a bigger one that are 144 kilobits. If I take this area and multiply it by how many of them are on the chip, and I add in the same thing for the 144Ks, it's for a typical member of this FPGA family, 20% of the area, and that would be typical of most FPGAs, right? So it varies a bit, but it's like a reasonable ballpark estimate. So it's a pretty important thing to get right. Okay, so you're all learning to be FPGA architects in these classes. So what you need to do is, the RAM architecture problem is you pre-decide what physical RAMs to build. Okay, so in an ASIC, you would basically wait and see, well, what's the design? And once you know what the design is, you would decide what RAMs to build. We can't do that in FPGA. We have to decide what RAMs to build in advance, and then people can configure the device, they can use different logic and routing, but they have to live with whatever we built on the chip. So if we build things that are not very useful, then they're going to not be very happy. Okay, so there are a bunch of choices here. So the first is, how many bits? Okay, so how big are each of these physical RAM blocks? Obviously, if you make a bigger RAM, it takes more area, but it also is more capable. Another thing that's important is the width of the ports. Okay, so the data bus that you use to write data to it and read data from it, how many bits can you get in or out in a cycle? So that's the width of the bus. That also, it obviously has benefits to have a really wide bus. Designers like that. They have high bandwidth to the RAM, but it costs more. And we need to think about how many ports. Okay, so ports is how many things the RAM block can do at once. So in one cycle. So the simplest, cheapest RAM you can build is what's called a single port RAM. So it has one read-write port. So in a given clock cycle, you can do a read or you can do a write. So you have a signal that says which one you're doing, but you can't do both. Okay, a bit more capable, but sometimes a bit more area too, is what's called a simple dual port RAM. So that's basically you have one port that you can read from and another port you can write from or write to. And you can use both in one cycle. So in the same clock cycle, you could do read one word, like read out what's in address 100 and write to a different word. So overwrite what's in address 38. And then a little more capable still is 2 read write, sometimes called true dual port. And that means I have 2 ports still, but I can choose every cycle to do 2 reads, 2 writes, or 1 read and 1 write. So that's a little more flexible. So I have to decide on all those things. We also have another choice in an FPGA. So we have these LUTs. And these LUTs actually have a fair amount of memory in them. So if we look at that fracturable 6 LUT, that ALM, it actually has 2 registers in it in Stratix 4, but it has 64 configuration RAMs. So it has a reasonable amount of SRAM embedded in it. A lookup table actually is a read-only memory. So if we could find a way to write that we could actually turn that LUT into a RAM. And that's often called LUT RAM, and that can be a useful thing too. Okay, so RAM mapping. So this is what you're doing for assignment 3. So most FPGA CAD tools don't make designers choose these exact physical blocks. Okay, you can do that if you want. You can instantiate low-level IP cores and say, I want this M9K, I want this M144K, and now I'm going to go hook them up myself. So you can do that, but most people don't. What people generally ask for, either by asking for an IP core or just writing HDL that represents a RAM, is what I call logical RAMs. Okay, so logical RAM is this is what my design wants. Okay, I don't care what's on the chip. I need a RAM that's 2,048 words deep. I want each word to be 32 bits wide, and I want to have 2 read ports and 1 write port. So in a single clock cycle, I can read from 2 different addresses and get that data out, and I can write to another address. This probably doesn't exist on the chip, but I want the CAD tool to go make that for me out of what does exist on the chip. So we have to map to physical RAMs. And I'm going to go through an example of how you map this. So let's say that our physical RAMs that we built 8 kilobit RAMs. And our 8 kilobit RAMs are organized as 1,024 words, and each word is 8 bits wide. So I multiply that, it's 8 kilobits. And I built 1 read port and 1 write port. Yeah?
Can you have multiple banks here?
You can build multi-bank structures, but that's on you generally. So, I don't know if everybody knows what a banked memory is. Does everybody know what that means? Okay, so a banked memory is basically, it's a structure where you say, I'm trying to think of the best way to describe this. Okay, so what is a banked memory? So a banked memory is a structure where you have multiple ports. So maybe I have like 3 read ports, okay? And those 3 read ports will go to different pieces of memory inside this structure. And they might map to 3 different RAMs inside, in which case, what are called 3 different banks, in which case you can actually do all 3 reads at once. But they might actually wind up mapping to all the same one. Okay, they all map to the same bank, which basically means the same physical RAMs. Then they're going to have to serialize. Okay, so that's called a banked memory structure. It's a way you can get more memory bandwidth without spending a ton of area. FPGAs generally do not build you banked memory structures, you build them yourself, okay? Because this is essentially this is like a logic structure that you'd have out here, where you'd basically say, take a look at these 3 addresses, see what what bank of memory they all map to, and decide whether they can proceed in parallel or if I have to serialize them. So FPGAs could provide a structure like that, but I don't know of any FPGA that does. They provide essentially this lower level structure of what are these actual RAM blocks, and you build, if you want a banking structure on top of that, you build it out of logic. Does that make sense?
So it depends on the designer.
Yeah, so the designer chooses, if I want to have that kind of bank structure, then you build it. And the basic reason is that the banking structure itself can be built pretty efficiently out of logic. And it's difficult to say what people might want. So that's a good question. But that's essentially like that's the next level up in sort of the memory design. The designer would decide how to do that. We are, kind of looking at we're looking at the actual just blocks of RAM they want. That's what these logical RAMs are. Does that make sense? Okay, so let's say that the designers asked for this logical RAM, but all we have are these physical RAMs. So they clearly don't match, right? If we try to use one of these physical RAMs and just say that's your logical RAM, we didn't meet the designer's goal. So how do we map this? Okay, so let's see so what do we do? See if anybody can do this. Alex might be able to do it, but I'm not going to ask him. Okay, what do you think? How would you do this?
I feel like you just need, you need to replicate the capacity 2048 by 32. So
Okay, so what are you going to do? So you're right, you need more capacity. Okay.
you can have 4 in parallel to get the 32-bit width,
Okay, that sounds good. So you got 4 of these in parallel. That gives you 32 bits. Yeah.
and then just replicate that structure to have 2 banks of that, or I guess they have two blocks.
Right. So then you're going to replicate it 4 more above it. Okay. And you're going to have to combine these somehow.
Yeah, the read and write ports, maybe you need some extra logic to, and like some decoders or encoders.
Yeah. So you are going to need some extra logic to tie these together, which I have on the next slides. But this is you're definitely getting it, right? So you're basically making a wider word because these were 8 bits wide. Whoops. So you said put 4 of them together to make me a wide word. And that's a good idea. And then you said, well, that's not deep enough because each of these was only 256 bits deep. No, actually, it's 1024. I'm not following my own instructions. So you said put 2 of them kind of stacked on top of each other to make this deep enough. We're going to need some logic to tie that together. Okay, so we'll need a bit of muxing and decoders. Each of these things is 1 read port and 1 write port. I actually want 2 read ports and 1 write port. Any idea about that?
I think you don't need that. So for 2 read, I think the logic that you build around should be enough that you don't, that 1 read, 1 write for each block should be, like if you're clever with routing, that extra read that the designer is asking for,
Mm-hmm.
I think you should be fine, but I'm not completely sure.
Okay, so you're hopeful you can do that cheaply, but you're not sure? What do you think?
I think like if each of these blocks is such that there is no clever switch left by Altera in there to kind of connect multiple blocks together, then you would just need to replicate it twice to have to.
Yes. Okay, so you're saying this gets me 1 read and 1 write, because that's what I had here, right? My physical RAMs had 1 read and 1 write port. And you're saying if I want another read port, I'm actually going to have to just duplicate that whole thing. It's quite expensive, but that's actually right. If I actually want to have a second unrestricted read port, I can read anything I want. I just need another copy of the data. So I've got this now more, so good answer. Together you two have definitely designed it. So let's go through this bit by bit. Okay, so I want this logical RAM. It's 64 kilobits, organized as 2048 words, 32 bits wide. And I have 2 read addresses, which I'm showing here, and 1 write address. I'm going to get 2 read datas. Okay, so read data are like outputs from the RAM block. And I'm going to have 1 write data. So that's an input to the RAM block. So this is what I want, but this does not exist on the chip. So I gotta fabricate it. So I got a whole bunch of these physical RAMs. They're only 8 bits wide. They're simple dual port, so I can read and I can write. But I don't have 2 of these read outputs. And I have 1 read address and 1 write address. And it's only 1024 words deep. Okay, so let's see. Let's look at how we built this. I'm just going to go through exactly what you guys told me to do. So the first thing I'm going to do is I'm going to take this piece of the RAM, and how do I build that? And that's the easiest part. Okay, I need a wider word. I just basically group together multiple physical RAMs, and I wire them to the same read address and the same write address, so they all produce part of my output data. And if I have to write data in, they sync, they store 8 bits each, okay? No extra logic. I just have to connect them all to the same read address and write address, and this is a very efficient way to make wider words because I didn't add any soft logic at all. And what I have now is I've got something that's 1024 words deep and 32 bits wide. Okay, so I'm closer to what I wanted, but I'm not all the way there. I basically implemented this gray part of my logical RAM, so I got half of it. Is everybody with me so far? Because if you're lost at this point, you're going to get more lost. Okay, so and then you will be lost on the assignment. So you might go, I'll be lost for 15 minutes. I don't care. I'm going to think about my happy place. But no, you will be lost for 3 weeks. So you want to ask questions if you get lost. Okay, so now what do I need to do? I need to get the other half of this. And you already gave me the answer to that. You said, okay, do it again, right? Let's stack this together. Okay, so now I've built that structure twice. So I've got 4 physical RAMs here, 4 physical RAMs here. I connect my read address to all of them. I connect my write address to all of them. So they each provide 8 bits. I get a 32-bit output from the top. I get a 32-bit output from the bottom when I do a read. And I send my write data to both of them. Okay, so far I haven't added any soft logic. I now actually have enough RAM bits, okay, because these RAM bits are covering this half of my RAM. I haven't put any logic in here. I've just wired things together. And I have wired them together correctly. But I have not quite done. What else do I have to do? I actually now do need some soft logic. One hint would be that my read data doesn't actually seem to go anywhere, right? Like it sort of notice it just kind of comes out here and then just stops. Okay, so that's a hint. Maybe I need something there. So yeah, what do you think?
Well, we need a mux to choose between the top half and the bottom half.
Right, so I need a mux here. It's got, my data is 32 bits wide, so I'm gonna need 32 muxes. Each of them only has to pick between 2 things. So 32 2-to-1 muxes, not too bad, right? I can do that with 32 basic logic elements, which is not free. Like that is gonna cost me, 3.2 logic blocks. So there's some area there, but it's not too bad. What should I control that by? Okay, so the data inputs are going to be from here and here. What's my select? Right, so I need to basically hook it up to a read address. Okay, okay, and I guess I did this in the opposite order. Okay, so that's the read. What about the write?
The write also would be sort of a demux where the top bit we select where which bank, I guess which half of the teacher.
Yeah.
It's 0 right to the bottom half, it's 1 right to the top half. So you'd also control by the top bit and write address.
Right, so this logical RAM had 1 more address bit, okay, on my write bus. I haven't used it yet, okay, because each of these only has 10 address bits. It's got 1024 locations. So I've hooked up the bottom 10 address bits to both of these. I need to use my last address bit, right? It's kind of a hint. If I just have a signal that goes in and I just threw it away, that's probably not legal. So I need to connect it to basically a write enable. All these RAM blocks have a write enable, and that's gonna decide, which of these 2 halves do I connect to. So if this bit is high, I'm going to write up here. I'm going to say this is the top half of my RAM. If this bit is low, I'm going to write to here, and that's the bottom half. This is cheap, right? 1 logic element. I just needed a single inverter. Yeah.
I think we need some more logic in there so the user still has a right enable to work with for the overall.
Yeah, I didn't bother hooking up. So if the user actually had a write enable, then I would basically AND that with this signal, okay? And I could do that. Does that make sense? So, yeah, so I'm basically doing this where the user didn't have a write enable, which means that every single cycle they're writing, if they do have it, I just put an AND gate and add in their write enable signal. Okay, so let's show the read. So the read path was not okay. Yeah, and that one was maybe even more obvious because it didn't actually exit the block. It only made it halfway out. So what we need is this 32 2-to-1 muxes. And now we have a proper read output, 32-bit read output. Okay. So, and this is not yet okay because we didn't do our second read address. Okay, so we wanted a 2-port RAM. I've only built a 1-port RAM so far. Yeah.
If we want 2 read ports, right, we can say the first read can be from the top bank, well, the top half, the second can be the bottom half, as long as we can guarantee that our reads will never overlap. And I guess a lot of the cases we're not doing random accesses, we're probably reading, what do you call them, like, let's see, the consecutive memory addresses.
Yeah.
So we can find a way to say, to interleave memory essentially.
Yeah, what you could then do is take one of your low order take one of your low order address bits and put it here, right? And take this highest order one and put it here if you were interleaving, right? If you decided I'd like to interleave on 64, I don't know, 64 word boundaries or something, then you might take your 6th address bit and put it up here. What you're describing is essentially a banked memory structure, right? That's actually what we were talking about before. So if you say, so I'm going to build we're going to build next a completely separate read port. So a two read port RAM basically means I can read 2 memory addresses every cycle, absolutely guaranteed. Okay? Give me any 2 addresses, it works. So it gives you a very nice contract. And things like register files, for example, like that. Because if you're starting to build like your processor control logic and it gets a lot more messy if you say I might be able to read like 2 or 3 registers, or maybe I can read 1, right? So that might hurt your processor quite a bit, and also in terms of throughput, it might make your control logic worse. On the other hand, if you actually need a whole bunch of read ports, you say I actually need 8 read ports, that gets incredibly expensive. So you are going to do what you suggested, which is you're going to say I'm going to bite the bullet. I'm going to accept that there will be times when my addresses conflict and I need to have control logic to detect that, and you have to stall and wait multiple cycles. But yeah, if you basically said, I'm not going to put this mux in, basically. What I'm going to do is I'm going to have 2 outputs, one from the top, one from the bottom, and as long as my 2 addresses go to both halves, I'll get both. Or like as long as my 2 addresses go to 2 different halves of the array, I will get both active. And if they go to the same, I'll only get 1 active. And that is a multi-banked memory structure, and you would have to have basically a valid bit that comes out here and you can stall. And those are extensively used too. Maybe next year I'll put that on assignment 3. At the end of assignment 3, you can tell me if it's hard enough, and if it's not hard enough, I'll put that on. But it's too late for this year. No matter how much you beg it to be harder, I just can't do it.
I was going to follow up with a question about, do these operate fast enough where we can double pump it? And
yeah, that's another good idea. So I'm going to talk about that in a minute too. Okay, these are all good ideas. So we could multi-bank it, but that essentially changes our logical structure. So not going to do that, because I'm pushing the problem to whoever uses me. And we basically have 2 methods by which we can build this second port. So I'm going to show you the one where we replicate, but you're right. The other one is to slice it in time to time-domain multiplex it.
And we can usually do that without sacrificing like that, Max?
Sometimes,
okay.
Right? So it is another valid design choice. Okay, so let me show you the one okay, so before I do that, I'll ask one more question. This is functionally perfectly correct. If I didn't need the second read address, I'm done, okay? And I actually can't beat the area of this. We basically use the minimum number of physical RAMs. If this is our only choice, we only have one kind of physical RAM, and I use the minimum amount of logic. So I can't beat the area of it. Do you think I could beat the power of this if I cared a lot about power? So I see you nodding. What do you think?
Because like one of the read, you're never using it, so either take the read from.
Yeah. So I am still wasting power, right? Because I actually am reading from both halves of the memory and then only paying attention to one of the 2. So the way logic works, you've seen this in the first 2 assignments, is when you toggle, you burn power, okay? So the routing, your logic gates, your logic elements, it's all about toggles. On a RAM, you're going to see how a RAM works internally in a few slides, but basically there's a pre-charge and an evaluate phase. So a RAM basically doesn't really care what data you read out. All it cares is, did you read me? And it cares, did you write me? Every cycle where you do a read or a read, it takes about the same amount of power, no matter what you're reading. And where you do a write, it takes about the same amount of power. So if you want to minimize the power of a RAM, it's all about not actually doing a read or not doing a write in as many cycles as you can. So we're already only writing to the proper spot because we had to do that for correctness, right? If we don't do that, we actually overwrite data we shouldn't. So for the write, we already have optimized it for power. But as you said, for reading, we're always reading both of these. And then we just don't pay attention to one of them. So a better solution for optimizing power, which I think I have in the animation here. Okay, I didn't show it. But a better solution is to actually hook up a read enable as well. So all these RAMs also have a read enable. And I could basically take the top read address bit. So I could take read address 1 of 10 and basically hook it up to a read enable here and invert it and hook it up to a read enable here. It makes no difference to the logical correctness of the design, but it is going to cut our read power almost in half. Yeah.
If my RAM doesn't have a read enable, will clock gating help or?
Yeah, I mean, clock gating will do essentially the same thing, but it's more messy. So gating your clock is just always, yeah, it depends what your RAM block presents. So if it presented a read clock and a write clock, and then it's okay if you have just a clock enable on the read clock, it essentially is an enable. Does that make sense? And yeah, if you only had one clock and you gate it, you have to think carefully about what did I just do to my write and so on. But normally they do have two independent clocks, so I guess a gate is pretty much an enable at that point. Okay, is that all pretty clear? All right, so the last thing we needed to do was make the second read port. And yeah, there's no better solution. Like if I need that full flexibility, if I can always for sure do 2 reads in one cycle, I actually have to duplicate the whole thing. I write my data to both. Okay, so I now have 2 copies of all my data. And I hook the read address 2, the second read address port, up to this second copy that I made and build everything the same way, all the same muxing, et cetera. And now I get my second read output. So that second read port was very expensive, right? I actually doubled the cost of my system. And you're right, there is another way you could do this. So instead of duplicating it, if these RAMs run much faster than your design, if they run 2x faster or more than your design, what you could do is basically time domain multiplex them. So you'll send in one read address in your first half cycle, and you'll get it out, you'll capture it on your registers, and then you'll send in the second read address on the second half cycle, and you'll capture it. So if you have the timing headroom, then you can do that. You do have to add a bit of logic, right? So you have to add, you have to have a double frequency clock that you generate, and you have to have in soft logic for most FPGAs. Most FPGAs, sometimes they have a little bit of hard logic for this, so they can actually make it easier for you, but most FPGAs don't. So you have to build the time domain multiplexing circuitry in soft logic, which is doable. It's not that expensive. So if you have 2x if these run twice as fast as your design, you can consider time domain multiplexing it. Yeah?
What about DDR?
So DDR is off chip, generally. So what do you mean by that?
Like I guess with DDR it's double data rate, so
Yeah.
what you receive positive.
Yeah, so time domain multiplexing does something similar, right? So DDR is doing that to basically make use of the limited number of data pins to a RAM. So inside the DRAM chip, it's not double data rate. In fact, it's kind of like quarter data rate. It actually has like a wider bus inside of a DRAM chip, and then it brings it out near its pins, and then it sends it out to you at a higher clock rate. And yeah, so DRAM chips use DDR so that they basically can run the clock half as fast and save like energy. So that's the basic reason they do that. When you time domain multiplex, you're building something similar, right? And there are a few different ways to do it. You could use the positive and negative edge of the clock. These RAMs are fundamentally positive edge triggered. So you have to get them 2 positive edges. Like you have to send them a clock that's twice as fast. Once it comes out of here, the normal way people do it is they have a 2x clock and a 1x clock, and they put in a little bit of logic to basically capture the data into 2 sets of both a positive edge and a negative edge triggered register on the 2x clock, and then transfer both of those to the 1x clock. So that's generally what you'd build in soft logic, which does look similar to the double data rate circuitry that you use to talk to DRAM. Any other questions on that? Yeah.
When I looked at some of the synthesis tools that actually do this mapping, they spend a lot of logic on conflicts. So read after write, write after read. So is this just assuming that we're just kind of saying whatever conflict happens, conflict resolution is whatever?
I've got so many ways I can make assignment 3 harder now. Yeah, okay, so if you're writing like the full synthesis and RAM mapping logic for this, when you have, okay, so if you have a multi-ported RAM like this, like I've got 2 read ports and a write port here, you do have a question of, well, what if I read and write the same address? Like, what happens? If you're using 2 different clocks, which is pretty common, okay, so often when you've got a read and a write, you're transferring data between 2 different clock domains, so not always, but sometimes. In that case, basically the CAD tool goes, you're on your own, right? They're 2 different clocks, I have no idea. Like, there's no way, if you read and write the same memory location with 2 different clocks, like, you get what you get and you don't get upset, right? If you're using the same clock for the read and write, which you might do if this is like buffering in your latency insensitive design or elastic pipeline, then you have a few options. What the RAM would kind of like to do, let me think about this. So what the RAM generally prefers is it gives you the old data, okay, and then writes over it after that. The reason is that tends to be faster, okay, because the read can happen while the write is happening. So if you look in the detailed IP settings or in the Quartus or Vivado settings, you'll find that you can actually control what happens during the read during write behavior. So you can specify on a RAM what should happen if that takes place. Most RAMs, for the maximum frequency of these RAMs, like what they'd like to do is usually what's called don't care. You basically just say, I designed, like in a FIFO, you really shouldn't be reading and writing the same location at the same time. Okay, that's kind of like your FIFO is empty, so just don't do that. And then you say don't care, and it means, I don't know, something happens, I don't depend on anything, and generally you can run the RAM faster that way. If you need to get the data, read the data that was there before the write, usually what happens is the RAM timing is slowed down by the CAD tool. Effectively, it has to complete the read before the write begins, so you'll actually get a slower clock frequency for the RAM. And there's another mode where you get the new data that you're writing to it, which usually also slows the RAM down because it has to make sure the data is written in, and then you actually read it. So those other modes give you more knowledge of what happens, but if you don't care, and usually you don't, right, you can design your logic not to care, the CAD tool can program the RAM to be essentially faster because it doesn't have to serialize the read and the write. Yeah.
So when you're using 2 different clocks for handling the reading and writing at the same location at the same time?
Yeah.
Yeah.
Then you have no idea what you get on any given clock edge if you don't know what happens.
Yeah, but the clock numbers should be prime numbers, right?
This is for you. This is for you to go off and think about. Like generally, like if I have 2 different clocks that are not, there's no synchronous relationship between them, etc., and you're saying they're writing to the same location, and when you get down to the details of the RAM, there's all these self-timed circuits. I'll show you a little bit of how a RAM works in a minute. But basically, you do not know what's going to come out the other side. And if you designed your logic assuming something's going to come out the other side, then your logic is just broken, right? Like it's just never going to work. If it's on the same clock, you can ask for specific behaviors. But if they're different clocks, every possible thing you can think of will happen. So, okay. So observations from this. So we can combine RAMs to make wider words with no extra logic. So that's very efficient. We can combine RAMs to make deeper, we can combine physical RAMs to make deeper RAMs with some extra logic, right? We needed a little bit of decoding, which wasn't too bad. We needed some muxing on the read path, which was a bit worse, but not too bad still. And logical RAMs that have more ports than the physical RAMs are very expensive. Okay, so we saw that if we needed 2 read ports and 1 write port, but the physical RAMs only gave us 1 of each, we actually had to duplicate the whole thing. So it doubled our cost to get that second read port. The write ports are worse. Okay, so if you actually go and say, what if I want 2 write ports, then you can't just say, I'm going to duplicate the whole RAM and write to both halves. So it's actually even worse. So yeah, they're pretty nasty. And actually, any alternative you guys have already talked about. So the alternative for getting more read ports and more write ports, this will work for both of them, is that if the physical RAM's fast enough, we can time-domain multiplex it. And usually that's soft logic, but there are a few FPGA vendors that put hard time-domain multiplexing circuitry right in the RAM so that you can do this with no extra logic. Yeah?
For dot product engines, which need 2 reads basically every cycle, how do they keep the area down while having 2 reads?
So a dot product engine, you need to have like a wide RAM, right? So one of the things that you often wind up with is it's not just how many words you have, like it's how wide you can get the data out. So if I have a dot product engine that can chew through, I don't know, 10 8-bit numbers times 2 operands, I got to get it 160 bits, 80 bits of data from one side and 80 bits of data from the other side every single cycle. So I would build probably a RAM, 2 RAMs with 80-bit words.
So it's essentially 1 read, but lined up so that they can be read at once.
Yeah, like if I'm doing a dot product engine where I know that maybe I got 10 8-bit values, but I know I'm going to use them all together, it's way more efficient if I can basically say, well, it's a lot more efficient if I can say, let's pack that into one 80-bit word. It gives essentially the RAM mapper a lot more flexibility. Does that make sense? Rather than I'm going to put that into 10 independent 8-bit memories. If they don't need to be independent, like they all have the same address bus. In fact, even if you wrote it, okay, so if you didn't even think of that, but you wrote your logic way back here, like if you basically wrote your logic where you actually made 10 different RAMs, they all have different data outputs, like their data outputs are all connected to different things, but their addresses are all the same, and their clock is the same. Quartus, for example, will say that's one logical RAM, right? Even if you didn't say it was a logical RAM, it goes, I know that's a logical RAM. This designer may not know it, I know it, okay? And it'll pack it more efficiently. Okay, so now I want to talk about choosing a physical RAM architecture. So that's how we do RAM mapping. And again, in assignment 3, you're going to get like a whole bunch of detailed legality constraints, and you'll learn how to do this. Okay, so in order to look at like how to make a good physical RAM architecture, we have to look at how we build SRAM. So for a single port SRAM, so the heart of any SRAM is cross-coupled latches. Well, it's a latch, sorry. It's cross-coupled inverters that form a latch. Okay, so this is a 1-bit SRAM. We take 2 inverters, we cross-couple them. So this has 2 stable states, right? We can have a 0 on this side and a 1 on the other, or vice versa. And then we need to be able to read that. To read it, we put a 1 on this word line. These pass gates get turned on. So our old friend, the pass gate, they show up in lots of stuff. And basically, whatever value is on here, if I've got a 0 here, that means that this inverter is trying to pull this node low. It's going to pull this bit line down towards ground. And if there's a 1 here, it means that the pull-up on this one is on. So it's going to try pulling this bit line up. Okay? So I'm going to pull these 2 lines apart. This one's going to go lower. This one's going to go higher. If I flipped what I had here, right, I had a 1 on this side and a 0 on that side, it'll go the opposite direction. Okay, so that's when I go to read it. And I guess maybe I should show you what happens when you write it. To write it, you basically do the same thing. You set the word line high, but when you're doing a read, you basically pre-charge this. So there's a bunch of timing inside of a RAM. You send a clock to a RAM, it internally generates a bunch of delayed signals so that it can synchronize a bunch of operations. One of those is called a pre-charge. So the pre-charge basically are strong drivers at the end of this bit line that will charge both sides to VDD over 2. And then when you activate the word line, it goes high. We start pulling these apart in one direction or the other. And at the edge of we basically replicate these SRAM cells in a 2-dimensional pattern. Okay, so my word lines are running along here, and my bit lines are running along here. And the way I determine, what did I store in this cell is I activate this word line. So you take an address, there's a decoder that figures out, okay, which row does that mean? So if it's address 0, it's row 0. Activate that word line. The bit line and bit line bar get pulled apart. At the top of the array here, we have a sense amp. So a sense amp is a differential amplifier. It detects which direction did this go in. Okay, so these SRAM cells are small, so they're pretty weak. These bit lines are fairly long, so they're quite capacitive. They're connected to a whole bunch of pass transistors. There's a lot of metal there. So we don't wait for these bit lines to be pulled to 1 and 0. They get pulled about 30 millivolts apart. And then basically the RAM, again, it generates all these timed signals. It activates this sense amp, which is a differential amplifier, which tells you which way were these bit lines going, right? And it gives you a 1 or a 0. So that's for a read. For a write, we don't activate the sense amp. We activate this write driver. So what the write driver is it's a couple of strong drivers, and it looks at what am I trying to write? Am I trying to write a 1 or am I trying to write a 0? And if I'm trying to write a 1, it's basically going to strongly drive this to VDD, strongly drive this to ground, and then the row decoder is going to activate this word line. Basically, these SRAM cells have to be designed very carefully. With this strong VDD and strong ground, these pass transistors are strong enough to basically overwrite the cell. They overpower the inverters, and it flips state. So you can see designing an SRAM is actually kind of tricky. If I have VDD over 2 on both sides and I activate the word line, I should not flip. Okay, I should just start pulling the lines apart. But if I do have these set to VDD and ground and held there by strong drivers, I should flip. So that's part of why SRAM design is actually pretty tricky. It is analog design. Okay, but basically, does that make sense? So that's how an SRAM works in a nutshell. You'll notice that all modern FPGA RAMs, you have to register the inputs to the RAM. The reason is there are all these timing circuits that are generated off the clock, so they don't know what to do if your axes aren't synchronized to a clock. Okay, so your outputs don't have to be registered. You can choose to register them or not, but your inputs must be registered because they don't know what to do if it's not aligned to a clock. Okay, so this kind of gives us our area model. So the more SRAM cells we have, the bigger this array gets. So that's part of our area. But then we also have peripheral circuitry. We have to build this decoder that looks at the address. We need one for the read. We need one for the write if it's dual port. And so it decodes the address and decides which word line to activate. And we need some circuitry for every data input or output bit, right? So if our word is like 8 bits wide, we need to have 8 sense amps, and we need to have 8 of these write drivers. Does that make sense? So I need an address decoder, and then I need read and write circuits. So these have to match basically my widest data path width. So if this RAM could provide 32 values, it has a data bus of 32, I need 32 sense amps, and I need 32 write drivers. All of those take area. Okay, that basically just says what I told you. And that's basically what I told you. Okay, so that was what I just showed you as a single port RAM. Why is it single port? Because I have one address decoder. I have one word line that is driven by the address decoder. So I have no way to make this thing do two things in one cycle, right? I can activate one row of the RAM. I cannot activate 2 rows of the RAM. If I want to build a dual port SRAM, okay, which most FPGAs do, what I have to do is I still need my 2 cross-coupled inverters. Okay, that's my latch. But I basically replicate my word lines and bit lines. So I build, everything in blue is what I just showed you. I have a word line, and I have a bit line and its complement. And I basically, if I want a second port, I build another word line, and I use it to control a second set of access transistors, which are connected to a second set of bit line and its complement. so what I've shown here has two read-write ports. Okay, they're read-write ports in this case because I'm a very careful analog designer, and I've made it so that I can do either reads or writes through these pass transistors, depending on whether I pre-charge these bit lines to VDD/2 or strongly drive them. And my SRAM cell basically increased in size. It used to have 6 transistors, now it has 8 transistors. So that's part of the cost of going from a single port SRAM to a dual port. The other thing I need to do is, before I just had one address decoder and I had one set of read and write circuits. Now I need a second address decoder and to drive the second set of word lines, and I need a second set of read-write circuits, sense amps, write drivers, to basically handle the second port's data input and output. Does that make sense? Yeah.
So on FPGAs, is a single physical RAM block, do they you do all the physical RAM blocks as dual port, or is it a mix, or?
So it is normally, so the most common one is it's done as dual port. So what I've just shown you here is the most common design in FPGAs. There's not a perfect agreement. So there was a company that's since run out of money called Tabula. They made a time-domain multiplexed FPGA. They made single port RAMs. So the RAMs were single port, but they made them very fast, and they put hard time-domain multiplexing circuitry around them so they behaved like an 8-port RAM. Okay, so that was as long as your logic wasn't too fast. If your logic was really fast, then they might only be able to use 4 ports. So that was an unusual design. They basically said, let's make only 1 port because it's the cheapest, but then we'll make the RAM really fast and we're going to time-domain multiplex it, and we won't make you do it. We'll put it in hard logic. This is the dominant design, that you basically build a true dual port RAM.
So you don't really have to worry, like, if the user, because you're building, I guess, like, if your IP, like, you go to courtesan instantiate IP, and the maximum ports is true dual port.
Yeah.
You don't have to worry if the user's doing, like, one read, one write, because every physical RAM block is dual port, right?
Yeah, so in, I think all of Xilinx's devices that I know of, and most other FPGAs, and almost all Altera FPGAs, it's basically this design, right? So 2 read-write ports. In the most recent Altera chips, basically because, I don't know if I have this on my slides or not, but basically this is a tricky circuit, okay? This is a tricky circuit because of the fact that I have to worry about, will I upset the cell when I read it, okay? If I make these pass transistors too powerful, I could actually have read disturb, which is bad. If I make them too weak, I might not be able to write it. So that's tricky. In Altera's last 2 generations, what they've done is they've basically changed this structure to say one of the ports is dedicated to read and one of the ports is dedicated to write. So they made, it's still dual port, but it's not like true dual port where you can do a read or a write on each port. It's like you can do a read on one and you can do a write on the other, which is a little less flexible than you can do both. Does that make sense? And I mean, I've never seen them publish. I mean, I can infer this from their data sheets, actually, like that's what they've done. I'm pretty sure the reason they did it is you save a little bit of circuitry here, then you can build one set of sense amps and one set of write drivers, and more importantly, you can actually you can design this so that one of these is intended only for write. It has bigger pass gates. One of them is intended only for read. It has smaller pass gates, and the SRAM gets easier to design. Because SRAM gets harder and harder to design as you go into like smaller process nodes with more variability. It's not just that their SRAM designers like won that in some kind of contract dispute. It is that it is getting harder. So, yeah.
Would Altera or Xilinx design the SRAM themselves, or would they just get it from the foundry?
They usually design it themselves. Okay, so in Altera, we designed, I mean, I didn't personally do this, but the company designed almost all its own RAMs. The only one that I know of, there's one chip where we bought a really big RAM, a 512 kilobit RAM, because as RAMs get bigger, they can get a little harder to design because you've got longer bit lines and essentially all these signal,
Altera won't like get a memory compiler from.
No, we normally basically design the SRAMs because there's so much of it on the chip and you do need some custom circuitry. For all the chips I was on, the SRAM was designed in Altera, except that one big block, and that one big block was a nightmare. I mean, it was one of those ones that was like considered, we bought it from an outside company. It was intended to save time and be more efficient. And then it missed when the chip came back, it missed all its frequency targets. And integrating it was a pain because I guess I think I showed you, oh, I haven't showed you this yet. But when you get to, I did a guest lecture at Waterloo. I showed them that. If you have a big block and it blocks all your metal, it's bad for your routability. And one of the challenges when you buy a RAM block from somebody else is how far up the metal stack does it block the metal. That RAM block blocked it pretty far up, so we couldn't get most of the routing across it. And it was big enough, it was like about 12 rows by 12 columns, that was noticeable. So it was a pain for the CAD tools. And then it missed all its clock frequency targets. And so, yeah, after that we designed even the larger RAMs we designed in-house. So I can't speak for Xilinx, but my guess is that it would be similar. That they probably design all the small ones and maybe the big ones too.
Can you do a refund?
I don't know. I wasn't the one who negotiated the deal, but yeah. But I guess it was not a happy thing. Okay, yeah. So I guess I talked about how much you get twice as much peripheral circuitry and you get 8 transistors per cell to go to dual port. You could go higher, right? You could go to like quad port and so on, but just the cost keeps going up and you have to decide if there's enough usage of that. Altera, before I joined them, did have one chip called Mercury where they put in quad port memory. People didn't use it that much, so they never did it again. So probably going beyond 2 ports is not that good an idea. Yeah.
How was that supposed to work if you didn't write at the same cell?
Yeah, so that's what I was talking about before with Alex. If you read and write the same cell at the same time, you have to like basically read essentially the data sheet and the CAD settings very carefully. Most CAD tools have detailed settings where you can say what happens in that case. So in the RAM, if you instantiate the RAM block, if you just write it in Verilog, it'll follow the semantics of what you wrote in Verilog. If you instantiate the RAM, there's some detailed settings where you can say what is the read during write behavior. Oh yeah, so the reason this is tricky if you read and write at the same time is it's not clear, right? Like what happens? I go to read and write this at the same time. Do I get the new data that's being written? Do I get the old data before it was written? Do I get something in between? If you don't do anything, you don't know, right? Like both operations are happening simultaneously and you don't really know what's going to happen. If you rely on some behavior, you tell the CAD tool and effectively it will slow down the timing to do whatever you ask for. If you say, I want the old data, it'll make sure the read is completed before it activates the second word line. But that actually slows your RAM timing down. If you say, I want the new data, it'll make sure that the write is complete before it activates the other, the first word line. Okay? So it can do all of those if you built enough flexibility into your RAM. And this is, again, one of the reasons that FPGA vendors often make their own RAMs. You kind of get all these like programmable sort of features that you often wouldn't have in an ASIC RAM. Like people would have just decided what do they want, right? Do they care about that or not? In an FPGA, it's programmable, so there are some timing circuitry here to generate when do I enable the sense amp, when do I enable the word driver, and there are a few configuration bits that will tell it, oh, you have to slow down because the user asked for the read to be completed before the write starts. It's undesirable to do that, so if you don't care, and usually you can design your logic so you don't care, it's better to just not select those things. Does that make sense? Or you select what's called don't care.
So the tool will make sure you don't have to do what exactly at the same time.
It can't do that because if your logic just activates 2 lines at the same time, that's your logic. The tool can't change that, right? So you decided whether you ever activate the same thing, and then you decide whether you care what happens in that case. Yeah, so it does depend, what are you building? If you're building a FIFO, what you normally do is you build your logic of where the read and write pointers are so that never happens. And then you basically tell the CAD tool, or often its default is like don't care because it makes the RAMs faster. So they're kind of like, if you have no idea what this means, then I'm just going to make the RAM fast. And if you know what you want, you tell me what you want. Yeah.
Sorry to remain on this, but like, if you want the new data, can it just bypass everything, give you the data on the write port, and then happily write it later?
Yeah, so there are multiple ways you can do this. So one way, okay, so, so this is a good question. Okay, so the question is, I said to get the new data that's flowing into the RAM, if you cared about what happens if I read and write to the same location, so they're both going here. I'm saying one way you can do that is essentially serialize the read and write, slow things down. There is another way you can do it. If you say I want the new data, you can build bypass logic. So you can build logic down here that basically compares the addresses of the two ports, and if they're equal and one is doing a write and the other is doing a read, and you said I want the new data, it can forward that new data. Okay, so in that case it doesn't have to slow the RAM down, but you did have to build more extra circuitry down here. Or if you didn't build that circuitry, because that's actually a judgment call, do you put this extra circuitry in every single block RAM when most people probably are not going to use it? What you can do is you can have an IP core that builds it in soft logic. All those solutions exist. Okay, so you can do any one of those things. But yeah, I always like people who just said don't care, right? If you kind of like, I don't know what any of this means, just say don't care. So, okay, so what's our cost? So larger RAMs are more efficient per bit. Okay, they're quite a bit more efficient per bit, and the reason is, like basically all this peripheral circuitry grows sublinearly. Right? So if I make a really small RAM, I'm dominated by this peripheral circuitry. If I make a really big RAM, I'm dominated by the bits. So if I want to get the lowest area per bit, I should make a big RAM. And yeah, it amortizes everything else. So in assignment 3, you're given a simple cost model. Basically, the area of a RAM is mostly some constant times its bit count. So more bits, it takes more area. But there's another constant times basically the square root of the bits. That's basically that periphery around the outside. Sensams, the write drivers, the row decoders. There's another small constant, which is basically just all that timing circuitry. Like I told you, you got to like take the clock and you got to wait like 300 picoseconds, and then you got to activate this strobe that says activate the word line. So there's some cost to that, but it doesn't get bigger as the RAM gets bigger. And then we're in an FPGA, so we always have to care about how do we connect the inputs and outputs to the programmable routing. So there's another reasonably large constant times the number of route ports. Like what are we going to connect to the routing? Okay, so what this means though is if I wanted to maximize how many bits I get per unit of silicon, I should make my bit count really big. Okay, and then the asymptote is I would just pay C1 for every extra bit. All the rest of this would start getting amortized to 0. The thing that stops FPGA architects from going to extremely large RAM is there's a higher and higher chance of wasting lots of bits. So I made something that's very efficient per bit, but it's also really big. And if people just don't need a RAM that big, I waste most of those bits. The other way you can waste the bits is, okay, so one way is people might just want a small RAM. So I build a RAM that's 512 kilobits, and you only need like 128 bits. So you're going to waste most stuff. Another way people waste memory is maybe I actually need a RAM that has 512 kilobits of RAM in it, but it also needs to be a 1,000-bit wide data bus. So I need 512 words, but each word has to be 1,000 bits wide because I need them to feed some very parallel pipeline. If I built a 512 kilobit RAM that only has a 64-bit wide data bus, again, I have to stack a whole bunch of those in parallel. So I can't use it all. Even though a person wanted a lot of bits, they wanted a lot of bits, but they needed a lot of data ports. And I didn't build enough data ports. So we have a trade-off here, right? Something that almost all FPGAs do is they also make the RAM more flexible by adding a little bit of logic to make the width configurable. Okay, so you have a physical RAM, and I just showed you kind of what the RAM core looks like. And the RAM core always has some natural width and depth. Okay, so maybe 1024 words by 8 bits wide. But I can always build multiplexers that have configuration cells controlling them. And I could let you ask for 1024 by 8 bit words. Or if I have a 2-to-1 mux that I just connect to one more address bit that you send in to me, I could give you 2048 words times 4, and so on, right? Or 8192 by 1. So basically the RAM is really getting 8-bit words internally, but before it goes out to the programmable routing, you've hooked up a few more address bits, and I use those, say 3 more address bits, and I use those to do an 8x1, control an 8x1 mux, and I actually just give you the 1 bit you want for the full address you asked for. Does that make sense? And that's relatively cheap, okay? I could even do that in soft logic, but it's so common that people want to use the RAM in these different modes that most FPGAs basically harden this multiplexing, so the RAM appears to have a configurable width. Within some range, right? Like there's some range of muxing they built. Okay, so this is kind of a complicated figure. I'm just going to give you like the highlights. Okay, so we have these input routing ports. Okay, so we have muxes that connect us to the routing wires. So that's part of our cost. We have these output routing ports. So our outputs all have to get connected in as well. Okay, so that's going to cost us. And we already talked about, this RAM core, which is pretty close to what you'd have in an ASIC. I'm not going to, this is basically one particular implementation of that programmable muxing. So this basically, you can go look at this paper if you want to look at the details, but this is basically an efficient set of muxes that are built to allow you to output an 8-bit word, or a 4-bit word, or a 2-bit word, or a 1-bit word. If you output a 1-bit word, you have to pick which one of the 8 bits you should output based on some configuration RAMs and some extra addresses that came from the routing. So don't worry, you don't have to like kind of decipher what all that is, but it's basically, that's not that big. Okay, so the reason I circled the routing ports here is now this leads to some, we're going to like do some quick trade-off analysis of how many ports we should build on our RAM. Okay, so we could build, simplest RAM we could build is a single read-write port. So it has one address bus, and it has one input, it has one combined read data or write data bus. Okay, it's the simplest thing we could have. We could only do one operation a cycle. So how many route, I'll do this one for you. Let's say how many route ports do we need to the programmable routing? Okay, well first, like what is this good for? Okay, so it's good for instruction memories for soft processors, good for constants. Like if you only read things, you don't write them, that would be a good use of it. It's area efficient, 6 transistors per bit. And the amount of routing ports, we need one address port. So we need address, maybe you've got like an 8-bit address, okay? So we need 8 signals to come in. And then we also need whatever its width is. So if it's got a word width that is, say, 32 bits, then we need 32 more routing ports coming in. We also need 32 output ports, okay? Because here I've shown it as like a bidirectional thing, right? It's like a read or write bus. We really can't build bidirectional things out of FPGA programmable routing, okay? So if we need to bring, even though logically you can say, well, we have a data bus here that's either my read data or my write data. What we really need is read inputs and write outputs. And those are going to be built out of separate programmable routing muxes, separate programmable routing wires, etc. So this is how many ports we get. Address inputs plus whatever the data width is, inputs. And then the outputs are whatever the data width is. Okay, so everybody with me? And depending on how big this RAM is, if this RAM's not that big, doesn't have many bits, this is probably more expensive than the whole RAM. So that means maybe you don't want to make the RAM too small. Okay, so now let's say I want to do simple dual port. So simple dual port's really useful. Okay, what it means is I have 2 addresses, read address and write address, and I have a read data and a write data. So I can basically I can do one read and one write every cycle. Okay, and the reason this is really useful is you can use it for FIFOs, which are really common in FPGAs. And how many, okay, so it's going to need, well, how many transistors per bit am I going to need? This is like a quick test of whether you've been following along at home. So,
8?
Yeah, 8. Okay, good. So we need more transistors per bit. How many of these routing ports do I need? So if I've got address inputs, right? So address, this is some number, right? Address bits. So how many of these address buses, how many routing ports do I need for address? Yeah, so you need 2 of them, okay? So whatever it is, if I've got 8-bit addresses, I need to bring that in twice, right? One for read address, one for write address. What about the data? How many data inputs do I need? Just need the read data width, and then for outputs, I just need the write data width. So I do need more transistors per bit. I do need a little bit more address ports. So instead of just 1 address, maybe 8 bits, I now need 2 times that. But notice I still need the same number of data inputs, right? I needed with data inputs before and with data outputs before. I still need that. So that's part of why this is very nice, right? The single port, I needed to have basically just as many routing data ports as if I do simple dual port. So that's why most FPGAs will build at least this as their kind of native RAMs. Okay, so true dual port is useful, and basically you have over time you might have an unbalanced read versus write demand. So that can be useful in caches. So you write them, but you read them more often. So having 2 read-write ports means most of the time you could do 2 reads. That could be useful. Basically anything where you do more reads than writes, this could be useful. You still only need 8 transistors per bit, although the design is electrically slightly more complicated. But you do need more you need more ports, okay? So we need 2 address ports, just like before. But now, in some cycles, I might do 2 reads. So I actually need to build 2 read outputs, and I might do 2 writes. So I need to build 2 write inputs. So if this is actually more, right? So I basically have 2 times these widths. Here was 1 times the width on my data inputs and data outputs. Now it's 2 times that. That actually is not cheap. And you could build quad ports. So yeah, Altera's 2 most recent devices actually build simple quad port. So simple quad port, yeah, it's basically good for register files. Like I need lots of read and write ports because I have lots of access to this central storage. Also for shared memory switches. So I'm doing packet switching. One way I can do switching is obviously with multiplexers. Another way is everybody writes into some shared memory and everybody reads out of that shared memory. And that actually realizes a switching function that gets more powerful the more ports you have. Because the more ports you have, the more things can be reading and writing. So you get basically a higher radix switch. So there are uses for having more ports. If you build simple quad port, you basically need 12 transistors per bit, and you need more input and output, okay? So actually, so Altera, I guess I kind of misspoke. They don't actually build a simple quad port, they emulate it with time-domain multiplexing, okay? So their most recent devices, most FPGAs build this. They build true dual port. Altera's most recent devices build simple dual port to make it a bit easier. And then Altera's most recent devices actually do have time-domain multiplexing circuitry. So at a reduced clock frequency, they can pretend to have 2 read ports and 2 write ports without you building an extra soft logic. So I guess there are examples of all of these things. But kind of the sweet spot of what you really build is kind of between these 2. And the true dual port is what people have usually built. Does that make sense? Whoops. Okay, let's talk a little bit more about this true dual port though. So the true dual port, it has the same number of transistors per bit, but it has more routing ports needed. And routing ports are expensive in FPGAs. So what most FPGA companies do is because like the number 1 use of RAMs is actually in that simple dual port mode. 1 read, 1 write, because that's what a FIFO needs. So most things can use 1 read, 1 write. Not as many things need this true dual port where you go back and forth between read and write cycle by cycle. So it's not cost effective to build all these extra routing ports just to enable true dual port. Uh, but what most FPGA vendors do is they basically they build a true dual port RAM core. So the RAM itself does have 2 read-write ports. And what they do is they just don't build all of the data ports that a true dual port RAM would need in its widest width. So they basically build the amount of, they basically build the number of input and output ports that they would need for the widest mode of the RAM, say 32 bits, in simple dual port mode. And then for true dual port mode, they'll say you can use it, but you can't use it in the widest width. You can only use it up to, say, 16 bits wide. And the RAM itself could do 32 bits in true dual port. We just didn't build enough interface to the routing to do that. But you can use it up to half its maximum width as true dual port. So, and that still means you could use all the bits as long as you can live with a narrower word. Does that make sense? And yeah, this just basically says what I just said. Okay, so that's it for block RAM. So hopefully you kind of understand the constraints. Any questions on that? Cool. Yeah.
So like when you can, I guess, customize block RAM into different sizes. I understand for read, that's easy to do with some multiplexers, but when you write to it, then what about the extra bit that we're not supposed to?
You basically, okay, so you're saying if you need to make it deeper, is that what you're saying? Like, so let's say,
Yeah, so
oh, for configurable width, they basically have demuxes in there as well. So they basically build program inside the block RAM itself. It will have some multiplexing on the read output path, and it essentially has some demultiplexing on the write input path. So if you put it in a mode where you say this RAM is like, I don't know, 32 kilobits, 32,000 words deep and 1 bit wide, but internally it really is like 4,000 words deep and 8 bits wide. It also has a demultiplexer inside the RAM on the write path, and it will basically it will only write to the appropriate column. Okay, so it'll activate the word that stores the 1 bit that you want to overwrite. And then I showed you there are write drivers at the top. Instead of activating all 8 write drivers, it will actually activate only 1.
Okay, so it can do per bit.
Yeah, so it has to have on the read path, it has muxes to select from your read addresses which is the right subword. And on the write path, it has enable signals on the write drivers to only write to the right subword. Does that make sense? Yeah.
I'm curious, what is typically the widest word width that a physical RAM block will have in it?
Yeah, so you're actually going to learn way more about this than you ever wanted to in assignment 3, because you're going to investigate that exact question. If you look at commercial FPGAs, a common word width would be, say, 32 or 36 or 40 bits for a RAM that is 20 to 36 kilobits, so kind of a medium-sized RAM. And then if you go to the Xilinx, for example, has these really big 288 kilobit RAMs that they call ultra RAMs, and those have wider word widths. I forget if they're 64 or 128. So it's actually one of the things that's asked on assignment 3, but I'll give you a hint. It kind of makes sense that if your RAM gets bigger, you make the data bus bigger, because your cost of making the data bus bigger is amortized by the fact that the RAM itself is more expensive. And if you didn't make the data bus bigger, there's a higher chance that you sort of strand some of those bits. So basically people look at this experimentally. They do it exactly what you guys are going to do. You build a CAD tool and you go look at it. But intuitively, it makes sense that if you build a bigger RAM, you probably want a somewhat bigger data bus, although you may not want it linearly bigger, right? So if the RAM's 8 times bigger, do you want an 8 times bigger data bus? Depends how expensive the data bus is. That may not make that much sense.
So adding kind of like if you want to add one more row, which would be like one more word,
Yeah.
extend the RAM, that's kind of orders of magnitude cheaper than adding one more bit of width to the RAM, I guess.
It's not necessarily orders of magnitude more cheap.
But then, yeah, but like for an M20K, for example, you're saying like you have a 40 wide
Oh, okay. You're saying yeah. So you're not going to make like a 20 kilobit RAM with like a 10,000 bit interface. So
like
yeah,
square
uh, to,
aspect ratio or something.
you can kind of imagine it that like the RAM becomes incredibly inefficient if your data bus was bigger than sort of the square root of the RAM. Like it just starts getting hard to even physically realize it because it's kind of a two-dimensional structure inside. But then even beyond that, you have to connect into the programmable routing, and those routing ports are pretty expensive. So it pushes you towards somewhat narrower data buses, and what stops you is at a certain point you make them so narrow that you can't fill the RAM. So you've basically built all these bits and nobody wants them, right? Like only somebody who wants a ton of words could use them. But lots of pieces of a design only want a moderate number of words, but they need the words to be wider. Does that make sense?
Yeah.
And if you wanted actually just like a few words and they're not very wide at all, then you'd want a really small RAM. But those really small RAMs, stitching them together to make a fairly large logical RAM will be quite inefficient. So you do have a kind of classic trade-off where there's no perfect solution. Okay, so let's talk about one more kind of RAM idea. So LUT RAM. So everything we've been talking about is called block RAM, right? You built these hard blocks on the chip, you can use them. But the lookup table we have, let's take a fractional 6-LUT, so which, again, Altera and Xilinx are using. So a 6-LUT is a 64 deep, 1-bit wide ROM. And notice that it actually has more SRAM than a 4-LUT, so 4 times as much SRAM. And that makes it kind of more desirable to try to reuse as a RAM. To use it as a RAM, we have to be able to write it, okay? We can't just read it. So is that worthwhile? Okay, so it depends on what do we have to add, right? We don't want to make our LUTs too much more expensive because we're literally building, 1 million or 2 million of them. So we don't want to make them too expensive. So we want to keep it cheap. So let's just take a fractional 6-LUT. We already have all of this, right? We have 64 bits of storage. We have a MUX, which is our read path, right? You think of a LUT if you present like inputs and you get an output. Well, that is a read, okay? And if it's a fractional 6-LUT, we actually have another mode where we put it in 2 5-LUT mode, and basically we hook the same inputs up to both 5 LUTs, and we basically get 2 bits of output, and we have 32 words. Okay, so a fractional 6-LUT naturally gives us already 2 modes. 64 words, 1 bit wide, or 32 words, 2 bits wide. And we actually have the read path. We don't need to build anything. What we don't have is the write path. There is a path to write these SRAM cells. I showed it at the very start of the class, where you have essentially shift registers that gradually bring in some data, gather it up, and then you activate essentially a word line and you write a whole column of the FPGA. There are kind of variations on that, but that's the basic idea. So that's what we do when we power on the chip, but we can't do that while it's running. If we did that when it's running, well, it's just kind of bizarre. From a designer's point of view, it's like I just wrote the following, like part of the following 1,000 LUTs. Like that doesn't correspond to anything that you could write in HDL, right? That doesn't give you a write path that makes any sense to you. So we need to build a more normal write path where we can just say, update this 1 LUT. Okay, so how will we do that? So we have to add the low-level write circuitry, and we have to get the data in. So we have to send in, let's say 6-LUT mode, we have to send in a 6-bit write address, and we have to send in 1 bit of write data, and we have to have an enable signal. And if we have all those things, we could write a single bit of this. In the fractured mode, we would send in 5 bits of address to select one of the 32 words. We'd send in 2 data bits, and we're going to update 2 bits because we have a 32 deep by 2 wide RAM. But if we add these to our logic, we used to have 6 bits, like our 6 LUT inputs are essentially our read address, so those already exist. But I just added another 6 write address bits and a write data, like a data input. That's 7 more bits. So that actually takes me from, that means I need a total of 13 routing ports. Before I needed 6, now I need 13. So that's expensive. If I do the same analysis for the fractured mode, it's maybe not quite as bad, but I go from 5 bits that I needed to 12. And I don't actually have that many routing ports, right? Neither Xilinx nor Altera actually builds that many routing ports for one of their 6 LUTs. Xilinx builds like 6, and Altera builds 8, but that's not 13. And the cost of adding another 5 routing ports is a lot, okay? So that doesn't look appealing. Okay, so what would you do? Yeah.
Only use the top half of the practical lab.
Only use the top half. Okay, let me think about that. Okay, so what does that save me though? That means that I don't send in 2 data bits, I send in 1 data bit. Is that right? So I basically go down in this mode from 12 to 11, but it's still too much, right? I only have 8 routing ports in Altera and fewer in Xilinx, so it's still too much. And I just lost half my bits, so I don't like it. So, any other ideas? Yeah, what do you think?
Can you only use the LUT RAMs for ROMs and then get an initialization file that preloads it?
You can, but that is effectively what a LUT is, right? That's what your LUTs are. They are being initialized and then they're being used as ROMs. So in order to basically use them now where they're, let's say, making a register file out of them, I need to be able to write them. So any other ideas? Yeah?
Instead of just doing it for one BLE, you do it for the entire group of multiple BLEs.
Yeah, so that's exactly what basically both Xilinx and Altera do, is instead of trying to convert one BLE at a time, let's convert a group at a time. And if we convert a group at a time, we can force them to share some inputs. That is a restriction, but it's not too bad. How many people really want a 1-bit wide RAM anyway? Maybe there are a few, but we just don't care about them, right? Like so. And they also if it gets small enough, they can still build it out of registers. So once you get down to like, I need 3 bits of RAM, fine, go use the register. Okay, so what Altera does is they basically take the whole logic block and they convert it all at once to a LUT RAM. So the cost is you can't mix logic and memory in one logic block, but that's not that big of a cost, right? And the alternative is you just wouldn't do this at all. So what they do is basically, if you take this ALM and we look at the 6 LUT mode, we have 6 signals that are our read address. Okay, so those are used. We take the 7th routing port, we hook it to the write data. Okay, so that's the data. What are we going to write when you do a write? And we donate one of our routing ports to get one of our write addresses. Okay, and I have 10 of these ALMs. So if they all donate one routing port, that's more than enough to bring in 6 bits of write address. So we just group those together and broadcast them to all of the ALMs as their write circuitry. If we look at the fractured mode, we need 2 bits of write data, but we only need 5 read address bits in that case. So it's still only 7 inputs. We can still donate 1 routing port for a single bit of the write address. If we do that over the whole logic block, we have enough to bring in the whole write address and also a write enable. Okay, so we got everything we need. So now we write the whole thing as a unit. So basically all recent Altera devices do this. The read path is when you use a logic block as LUT RAM is just the regular LUT inputs. Nothing is added. When you use it as LUT RAM, you basically bring in the extra signals, a few per ALM, and then broadcast them across the whole logic block. It amortizes all the extra control circuitry. It means we don't need to add any extra routing ports. As I said, it means we can't mix logic and LUT RAM in one lab. You're either one or the other. And what you wind up with now is you can have a 64-word by 10-bit wide RAM or a 32-word by 20-bit wide RAM. So it's good for small RAMs, right? Not great for really big ones. And you naturally get 1 read and 1 write port. Compared to building the RAM out of registers, this is actually 30x more dense if what you needed was exactly this. Okay, so if you needed exactly this size of RAM, which maybe you don't, but then it's 30x better than just building it out of registers and the programmable logic. Now, block RAMs, remember we said were 200x for like an 8 kilobit block RAM. So for a large RAM, this still isn't as efficient, but for small RAMs is much better than building it out of logic and registers. And if you need only a small RAM, a block RAM might be mostly wasted too. So it adds a good flexibility. The other thing it gives you is you actually now have something that can be either logic or RAM. And that actually helps you with, some designs might be limited by logic, some designs might be limited by RAM. So if you have something that can morph between the two, it is better than something that has to be one or the other, because just flexibility has some value. Okay, so Xilinx does a very similar thing. They basically have one write data bit. Okay, so their fracturable LUT has 7 inputs. Okay, when you include the LUT plus what goes into the registers. So they basically, in 6 LUT mode, they use the 7th input to bring in their 1 bit of write data. In dual 5 LUT mode, they use the 2 extra inputs that they have to bring in the 2 write data. But they don't have anything left because they don't have quite as many route ports per basic logic element to actually bring in the right address. Okay, so they still don't have quite enough. So what they do is if you're going to use a single read-write LUT RAM, okay, so you only need 1 port, you can either read or you can write, they actually will just hook the read address up internally to the write address. Okay, they don't need to bring another one in. They'll just reuse it, so that's fine. And in that case, they can convert all of their LUTs, and they can build basically a 64 word by 8-bit. Their logic block has 8 things in it for most of their, Versal actually does 32, but for most of their chips, they have 8 LUTs per logic block. So they can do a 64 by 8 RAM or a 32 by 16. What do you think? Okay, so they actually do something reasonably clever if they need to do like a simple dual port. So I told you that simple dual port is more important than single port. It's used, you're going to find in the benchmark set that I give you for assignment 3 that about 80% of the RAMs are simple dual port. And that is real. So this is nice, but it's not dominant. Simple dual port matters more. So they do support simple dual port. What do you think they should do? So this clever trick for single port. They have another trick for simple dual port. So let's see if you can be as smart as whatever Xilinx engineer came up with this. So what do you think? Okay, well, you could do that. You're not supposed to do that, actually, because you get double damages if they can show that you actually, it's double or triple damages if they can show you knowingly infringed a patent. So most companies actually tell you to never go look at another company's patents. So it kind of defeats the purpose of the patent system. But so, yeah.
Things have the read address bits and write address bits.
Sorry, what do you mean?
Like, if I have six read address bits, I use 3 of them and read address bits and 3 of the write address.
Okay. Oh, so you're basically saying, oh, okay, so just make it less deep. So you say, instead of getting a 64 deep, you'll get 8 deep because you'll split the address. Yeah, they do something similar to that. But what they do instead of splitting the depth is they go, well, instead of having a by 8, I'm just going to take the inputs that would have gone to the 8th LUT, and I'm just going to say the 8th LUT is not going to get used. Okay? So it's the same idea, but what they do is they steal 1 LUT's inputs, which are sort of hardwired as its read port. And that means they can't use that LUT anymore for the LUT RAM, but they get to reuse all of its inputs. So what they can build is a 64 by 7 RAM if they're doing 6 LUT mode, or a 32 by 14 RAM if they're doing 5 LUT mode in simple dual port. So basically the last LUT became unusable. You stole all of its inputs and used it as the write bus. Does that make sense? Okay, I think we'll stop there for a break. Any questions so far? We're almost done with RAM. We're going to go through a few more RAM things, then we're done with RAM. So, okay, let's take a break till 5 after. And you grab as much candy as you want to invigorate yourself. Let's get going again. Okay, so we're almost done with memory. I'm going to tell you about, okay, so in assignment 3, the architecture that you're to assume in the first part of the tool, or first part of the assignment where you're basically mapping to a fixed architecture, is basically the same as Stratix 4, okay? And that is half of the labs support LUT RAM in the way that I just talked about. And why do you think only half of the labs support LUTRAM actually? Like, yeah.
Since you've taken away logic, like placing logic in the left, so you probably don't want to like have all of your design be able to support LUTRAM.
Yeah, but you can still do logic in these, right? Like they flip back and forth, like it's configurable. So this half of the logic blocks can be turned into LUTRAM if you want, right? One at a time. The other half cannot. They can only do logic. Why do you think they did that?
I think if you're going to be using, like let's say 60% of your design is LUTRAM, then you're probably doing a very high data, like intensive workload, and you're probably going to need logic for that.
Yeah. See, it basically just think there's no way somebody's going to use 100% of their logic as LUTs, right? LUTRAM. And that's basically it. It adds about 15% area in this architecture to add the right circuitry. So it's not free. It's not extremely expensive, but it's not free. So they didn't add it to every single logic block because they just go, well, not everybody's going to use it. 50% means it does complicate the layout. You basically need to make 2 layouts for the logic block, one that supports LUTRAM, one that doesn't. They do it in pairs. So it's basically like one column that supports LUTRAM, one that doesn't, so they have a replicable structure at least. So they spend a bit of extra non-recurring engineering effort to make 2 variants of the logic block in order to get a slightly more efficient architecture. And then they have, and this is not uncommon. So there's a lot of FPGAs that do the same trick of you have half, approximately, sometimes a quarter of your logic blocks that can support LUTRAM. And there are FPGAs where none can support it, and there are FPGAs where 100% can support it. But it's another knob. It has 2 kinds of RAM. So M9K blocks, so 9 kilobits, and M144K, so 144 kilobits. In assignment 3, kind of round those off to powers of 2, so it's 8 kilobits and 128. The reason for the extra bits is that these RAMs support error correction, and when you do error correction, it's nice to have parity bits. So you don't have to use these extra bits as parity bits. You don't have to use the ECC at all. And then you actually can use 9-bit words and 36-bit words and so on. But that's basically why there's these kind of funny numbers, right? Is that they work out well when you have error correction turned on. And you turn on the error correction in some high reliability scenarios where you're worried about basically radiation-induced bit flips, right? You can actually correct them. So yeah, this is close to the assignment 3 architecture. And I think there was a question. So did the question already get answered, or okay? Yes? No? Oh, yeah.
Does that mean Xilinx FPGAs don't have parity bits?
Don't have what?
Don't have parity bits?
They do. Their RAMs are 36 kilobits is their dominant size, actually. So, okay, so Xilinx RAMs, depends how you count it. I guess the way I would count Xilinx RAMs is that their main RAM in their recent chips is 18 kilobits, and that 18 gives you still parity bits, basically. Does that make sense? But again, you don't have to use them as parity bits, because a lot of the time in an FPGA, there's high parallelism in the high-end designs, so you actually literally can have 1,000-bit wide data paths. So if you go, I need to do a 1,000-bit wide data path, I can divide that by 18 just as easily as I can divide it by 16. So I can use all the bits, because I would need a whole bunch of block RAMs ganged up in series. Like ganged up together to feed that. Does that make sense? So the parity bits, what I'm calling the parity bits are useful even if you don't have error checking on. You just get a wider word. Okay, so let me go through. This is actually from the Principles and Progression paper. So if you read that, you know this table. This is just some examples to show what's efficient and what's not efficient in terms of mapping logical RAMs to physical RAMs. Okay, so let's say I've got a large logical RAM. So that's what the designer wants. The designer wants 2,048 words, 72 bits wide, so pretty wide word, lots of them, and they want simple dual port. So one read, one write. That perfectly fits a Stratix 4 M144K VRAM, like that exactly matches. It can do that perfectly, right? Using all its bits, using all its data outputs. So this is what it was made to do. So let's see what happens if you implement this. So if you map it to an M144K VRAM, it takes one of them, okay, because it's a perfect fit. The area one of the things I like about Stratix 4 again is that actually the area for its blocks are known. Okay, it's actually known because I published them. And what's that?
Legally?
I approved it. It was a grad student I was co-supervising who needed the data, so I approved the release of the data to him. But it is useful. We publish it, and then you can build on it. Okay, so we actually know how many millimeters squared that takes, and can compare it to the different options. Okay, so if we do this, it basically, we don't really care about the absolute millimeters, but just say it's 1 unit of area, and it runs at 336 megahertz. If you map that same RAM to 9 kilobit BRAMs, which also exist on this FPGA, you need 18 of them. Okay, so to get enough bits and enough output width. In this case, you're mostly limited by bits, but basically you can take 18 of these and put them in parallel and put them in one of their deepest modes, and it'll work. If you add up the area of that, it takes more area. It takes 1.9x as much area. It's actually faster. So the smaller RAMs do tend to cycle faster because the bit lines are shorter, the word lines are shorter. So in this case, you actually got a performance increase by going to that, but the area was about twice as big. So it's also a pretty reasonable choice. Like, it's not terrible. LUT RAM, we actually need quite a bit of ALMs. Okay, so this is like we need to have a bunch of logic blocks to get all the LUT RAM. LUT RAM can only go to 64 deep. Okay, so it can't go to 2048 deep. So we actually need to build a bunch of muxing in soft logic. So if you add and some decoding, if you add all that up, it's actually quite a bit more area, almost 13 times the area, and it's quite a bit slower, only 40% of the speed, because we have all that muxing, and we didn't pipeline it. I mean, if we could tolerate multiple cycles of latency, we could close the speed gap some by pipelining the muxing, but we didn't do that because that would change functionality. If we did it in registers, it's almost 83,000 ALMs, which is like 300 times bigger. And it also is relatively slow. So it runs at about 129 megahertz. Okay, so what is this showing? Like if you got a really big RAM like this, then this M144K was definitely the best choice, but the medium RAM's not terrible. Okay, and then it gets increasingly worse after that. Okay, but that's not, if that was all we had, if all we had were RAMs that size, we would just say build M144K RAMs and we're done. But we don't. Everybody does something different. So let's say we have another RAM that's more medium size. So say it's 1024 words and 8 bits wide, and it's again simple dual port, one read, one write. So in this case, it still takes one. If we put on the big BRAM, it wastes a bunch of the bits, it wastes a bunch of the output width, but it takes one of them. If we put in an M9K, well, this one perfectly fits an M9K. So, I mean, well, it's not quite perfect. It wastes 1/9 of its bits, but it's a pretty good fit. It takes one of those. And it takes 1/10 of the area of that M144K RAM. So it's much better for this small RAM. And if we put it in LUT RAM, it's not terrible. It's actually a bit better in terms of area than the big RAM. It is like 8x worse than putting it in an M9K. And I haven't included a case where basically something just fits in LUT RAM, but you get the idea. If I made a really small RAM, the LUT RAM's going to win. So this highlights, hopefully, the trade-off. Okay, these are some experiments from a paper that we won't read, but it's from the Stratix 5 architecture paper. And you're going to do somewhat similar experiments in assignment 3. So what this is showing is a few different RAM architectures. So this red line is showing what if I just built a block RAM that has 40 kilobits. The purple line is what if I did a block RAM that was 20 kilobits. And then this one, the diamonds, is what if I did a mix, 10 kilobits and 144 kilobits, some of each, which is close to Stratix 4, okay? And what I'm showing on the other axis here is how many logic blocks I have per RAM block, okay? If I have 2 RAM blocks, then it's how many logic blocks I have per sort of small RAM block. So if I have only 5 logic blocks per RAM block, it means I got a lot of RAM blocks, right? Like every 6th column is RAM. If I've got 21, like only every 22nd column is RAM. So I'm building a lot more logic and a lot less RAM. And then this is basically what is the total area of basically what's the area of the core, so forget the IOs, but the core of the FPGA, how big is it to fit a benchmark suite? So we average it across a bunch of designs, how big an FPGA would I need, how many rows, how many columns in order to fit it. And what this shows is, first, the 40 kilobit RAM is higher, okay? So it takes more area than the 20 kilobit RAM, so this magenta curve is better, or this one that's mixed, 20 kilobits and 144 kilobits, like some of each. So this RAM's too big. This one is a mix of 10 kilobits and 144. It's not quite as good either. So this is kind of the sweet spot. And it says you want around 10 columns of logic blocks for every column of these medium RAMs. Well, and then at that point, it's pretty close. You can either build a single 20 kilobit RAM type, or you could build a mix. So Stratix 5 basically did this. It decided to build 20 kilobit RAMs and about 1 column of RAMs for every 10 columns of logic, because that's basically what minimized the area over the design suite. They could have done this one, a mix of 20 kilobits and 144 kilobits, and basically the paper says the reason this was not done is it's just harder, right? If you actually have to make 2 kinds of RAM, it's more difficult to lay out, it's more expensive. So unless there's a gain, why not just do one type? And then this study said that one type was fine. So you will do this yourself as well, actually using the same benchmarks. So you have the benchmarks that were used for Stratix 5, and you can go off and with your RAM mapper see what kind of trends you find. Does that make sense? And yet, basically this is all trade-offs. If I don't build enough RAM, I wind up needing a bigger chip to get enough RAM, right? Because it's too scarce. If I build too much RAM, I wind up needing a bigger chip to get enough logic. So there's all this complicated trade-off space that you're trying to explore heuristically. Yeah.
Area, does it include like the routing?
Yeah, so the routing is actually included in the area of both the RAM and the logic blocks. So it's implicitly captured in all of this. Okay, okay, so how has this evolved over time? So this is also from that Principles in Progression paper. So if we go back to some pretty old Altera FPGAs in 1995, so before this, FPGAs didn't have block RAM, right? They just built it out of registers, or they had little bits of LUT RAM. And in 1995, Altera basically added block RAM, but it was small. It was 2 kilobits, so quite small block RAMs. And the number of memory bits per LUT, per logic element, was only about 10 memory bits per logic element. And again, before that, it was like 0. And then as you go forward, this is basically in capacity. So these are ever more recent process nodes, ever more recent, bigger FPGAs. You can see that basically the number of bits per logic element keeps going up. So there's a gradual trend upwards. These are the most recent chips. They're in like 14 nanometers and 10 nanometers. 10 nanometers has like the highest number of bits per logic element, so somewhere around 100 or a bit more. And you can also see the RAM architecture kind of hasn't fully stabilized. It keeps changing. So it tends to get bigger RAMs. So from 2 kilobits to this generation was actually 3 kinds of RAM, like really small, 512 bits, medium 4 kilobits, and that big one, 512 kilobits that we bought and was very problematic. Then this is the Stratix 4 generation, so a mix of 9 kilobits and 144 kilobits. And then the 2 most recent generations, or the few most recent generations, went to a single type of RAM, 20 kilobits. So there's a consistent theme here of the RAMs have tended to, on average, get somewhat bigger and you get more bits, but no consistent theme in terms of, what is the exact mix of RAM types? Now, Altera has converged on let's make one kind of block RAM. Xilinx has done the opposite. So for years, Xilinx had one size of block RAM, and in recent generations, they've actually said we'll have 2. So they have one that is 288 kilobits. So their kind of workhorse one is 18 kilobits, so not far off of this, but then they also added in a big one. So there's no convergence on exactly what the right RAM size is. Yeah?
Why did they choose to
Yeah, it's basically because if you just put like memory bits, you see an exponential curve, right? Like this is like how many LEs you have, and it's starting at less than 1,000 and ending at like many million. So basically, any trends would just be swamped by you see an exponential, because that is the dominant trend in all of semiconductors. If you plot everything on a chip, you'll always see exponential. But by normalizing it to LEs, what you're seeing is essentially what fraction of the area is being devoted to bits. Does that make sense? I mean, it's not directly, because you can get more bits per unit area by going to bigger RAMs, but it is saying designs are becoming more memory rich, and memory has become ever more important. You never know, in the future will that continue to hold, but probably it will. Yeah.
In a prior lecture, you mentioned that as the process knows it's better, we're seeing the RAMs aren't doing as well through the process.
Yeah, SRAM is not scaling very well, so which is not great news.
Is that reflected in this chart?
It is reflected in this chart, although the really bad RAM scaling problems are relatively recent, right?
Okay.
So maybe it's probably starting to happen at 10 nanometers, but it's getting worse generation by generation. It's not perfectly constant. Like TSMC, I think 2 nanometer did get some SRAM scaling over 3. But, well, it's 2 over 3, which is no longer really means 2 nanometers and 3. It just means 2 and 3. But SRAM scaling has been slower than logic and wire scaling recently, which is problematic. I have no perfect solution for that. Maybe it'll push us back towards 4 LUTs, for example.
Yeah.
Or maybe things that aren't LUTs, because SRAM, it gets expensive enough. You'll go, what can I do to try to minimize SRAM use? It's not that much you can do in block RAM, where what you're trying to provide is RAM. So you have limited numbers of options for that. Okay, I guess I talked about this a bit. So I've talked a bunch about Altera because I know it best, but in Xilinx, Vertex UltraScale Plus and Versal, so their 2 most recent generations, their RAMs aren't wildly dissimilar. So their workhorse RAM is an 18 kilobit RAM, and it has configurable width. You can go 18K words by 1, or 512 words by 36, or anything in between. And they do the same trick as Altera. It's 36 bits wide when you use it in simple dual port, but if you go to true dual port, they didn't build all the routing ports, so you could only go half that width, 18 bits wide. They have something extra. They have hard circuitry that allows them to take 2 18 kilobit RAMs and put them together into a 36 kilobit RAM. So basically means like that read path muxing and that little bit of extra decoding, they actually built hard logic for that. So they can group 2 RAMs together into a deeper structure with no soft logic. So you'll see in their literature, they'll sometimes talk about that they have 36 kilobit RAMs. They don't really. They have 18 kilobit RAMs with this extra hard circuitry, which frankly is more flexible. So if I was in charge of their marketing, I would describe it this way. But okay, and then they have these large RAMs, these 288 kilobit ultra RAMs. This one they might have bought. So a sign that somebody bought a RAM macro is if it doesn't have this configurability, because the configurability tends to be sort of FPGA special sauce. This one is 4,096 words by 72 bits, and that's it. And yeah, there is a trend as well in Xilinx devices to gradually increasing bits per LUT. So it shows the same trend, maybe even a bit stronger, because they have these really big RAMs in them. And if you're interested in further reading, so this is a paper that looks at the RAM mapping that I've been showing you is essentially an area optimized RAM mapping. How do we put the minimum amount of circuitry in? There are actually, if you change how you map to the physical RAMs, you can actually, at the cost of some extra soft logic, there are ways to save power. So we saw one, which was basically hook up the read enables, but there are actually a few other ones. If you're curious, you could read that. This paper is basically one on using a completely different style of storage element. So how do we get away from the fact that SRAM is not scaling that well? Well, you could basically use a different storage element. So this goes from the 6 transistors of an SRAM to basically 1 transistor and 1 magnetic tunnel junction, so a magnetic material. It gets 3 times the density for large BRAMs, but it's got a slower write speed. So, and a more complicated process. The big deal with doing something like this, where you get a more dense block RAM, But you need a novel process is can you get that process in a leading edge process node? Because FPGAs really like leading edge process nodes. It has a lot of very detailed diagrams of exactly how RAMs work and what their timing is and so on. So if you're curious about that, there's lots in there about how do you actually build a block RAM. And that is it for RAMs. Any questions on RAMs? One more? Okay.
This might be a really stupid question, but HBMs, are they considered RAM, or like could we like use them as RAM for the more modern FPGA?
Well, I mean, HBM is RAM, but what it's off-chip fundamentally. It's fundamentally an off-chip RAM technology. It's DRAM. Okay, so it's kind of related to this. It's not the same, but it's basically you store your data in a capacitor, and you have one transistor to access it. So it is more dense than SRAM by about an order of magnitude now. So maybe 10x better bit density. The process is incompatible with logic. To make a DRAM, you need to make deep trench capacitors and stuff, so it's fundamentally built on different wafers. High bandwidth memory means instead of basically putting a DRAM chip on a board beside an FPGA, you basically stack multiple DRAM chips on top of a controller chip, on top of an interposer, connect them with silicon traces through the interposer and up a 3D stack through all the chips. You get a very wide data bus of about 1,000 bits, and you can clock it at a few gigahertz, so you get much higher bandwidth.
And is this usually in a different discussion than the range we're talking about here?
Yeah, because it's an off-chip memory technology. It's basically, you would think of that in the same way as I'm thinking about what kind of DRAM do I put in my system. HBM is a kind of DRAM that gives you, so it's high bandwidth compared to DRAM on a board. It's low bandwidth compared to block RAM.
Gotcha.
But that probably would test very poorly in marketing. So, yeah.
They're also not putting like HBM stacks on your logic chip.
Directly on your logic chip without the controller logic chip?
Yeah, like make the controller in your logic chip.
Huh. Oh, that's interesting.
They try
Okay.
to do that.
Okay, interesting. Okay, so in that case, I'm going to go quickly on to the next kind of hard blocks, which we won't go into as much. Okay, so RAM's the most important hard block after logic blocks, but it's not the only one. So let's say I've got some idea for a hard block that I want to put in an FPGA. So maybe hardened PCI Express, for example, some protocol block. So the way that you should evaluate that is you develop the soft IP. So you can build it out of the current FPGA. And if this is an important enough thing for you to consider like hardening, you probably should have soft IP already. From that parameterized soft IP, well, you can just map it to your chip, and you can get area, power, and speed today using the regular fabric. You can take that same soft IP and basically say, well, let's harden it. And to harden it, what you usually have to do is add some extra muxing and configuration to it. So soft IP will normally have a bunch of parameters, and the CAD tools or IP generator will just build what you need. So PCIe, for example, there are many generations. So maybe Gen 1, Gen 2, Gen 3, you want to support all three. One way to do that would be to basically take all three versions of this IP and have a multiplexer and some SRAM cells, and you just build all three and mux between them. You might be able to be a bit more clever. You might find some sub-blocks in here that are shared, so you pull out some common logic. But after you've done this, mapped it to an ASIC standard cell technology, you get the area, power, and speed. You have to make sure you include the area cost of hooking this up to the programmable routing. So a common mistake people make is they just take the area of this, and they forget you got to hook up to the programmable routing. So, but that can be expensive. It has a lot of inputs and outputs. After you've done that, you estimate how often people will use it, and you basically decide it's a net win. Okay, so when they use it, it's 3 times better, but I think only only 10% of our customers will use it. Okay, that's a net loss. But if half of our customers are going to use it, then that's a net win. The estimating usage can be, if everybody's already using it, right, then you kind of know. But if you're trying to get out ahead of what they might use, then that's a lot harder. Okay, so let's look at one of an important hard block, so DSP blocks. So DSP blocks, so in Altera, I was part of the team that did that analysis, and I guess I told you some of the answers before, but it came out, this looked like a good thing to harden. In the DSP block, you have to pay a lot of attention to routing ports. So this is an array multiplier. You're not going to be able to see all the details, but it's basically the way you would do multiplication with pen and paper, right? You get a row for every bit, you get a row of partial products times, which are, you know, the AND of that bit in one of your inputs with all the bits in the other input. And you basically, you go to the next most significant bit, and you get another row of partial products that's shifted over by one, and so on. And then you add them all up, and you get your output. So this is basically the way you do multiplication with pen and paper in base 10, right? So this probably, hopefully should look like what you remember from, I don't know, grade 5 or something, but you do it in binary. The key things I wanted to pull out of this is that for an n by n bit multiply, I need n squared of these partial products. And these partial products, they're basically AND gates, and then I add things together. It's basically n squared of these basic logic elements. So this n squared is important. It means that if I'm doing multipliers that have at least a fair number of bits in them, this thing gets pretty big. And multiplication is pretty common, so this is a good candidate to harden. The other thing I want to check is, well, does it look like I'm going to be dominated by routing port area? So I check how many inputs and outputs I have. Well, I need two inputs that each have n bits, and I produce an output that's twice as wide, so 2n outputs. And the number of elements I need, like partial products, which turns into basically how many basic logic elements I need, is n squared. So this looks pretty good. At least if n is reasonably large, I shouldn't be dominated by the routing, because my compute is growing quadratically. Okay, so that basically is part of like thinking, well, this looks like a good candidate to harden. This is an 18 by 18 multiplier. So I got two 18-bit inputs, input A here, input B here. My outputs are coming out here, and these are all partial products that are getting added up. Okay, so I can just build this 18 by 18 multiplier. And if I think 18 by 18 multiplication is common enough in FPGAs, this should be a pretty big win. But looking at this, do you think you can use it for anything else? And it's actually color-coded that gives you a hint. So this is taken from a figure from a paper, so the color coding is a hint that, yeah, maybe there is something else you could do here. So what do you think? Like in an FPGA, you're always trying to build things people will use. If you can add some programmability cheaply so it can be used for more things, that's good. Now you don't want to add programmability in a really expensive way. That might be stupid. But if you can do it cheaply and make it more flexible, that's good. So if you look at this 18 by 18 multiplier, do you think there's anything else we could build out of it? What do you think? Yeah, so you can divide this up. Multipliers can naturally be divided up with a little bit of extra logic into smaller multipliers. Okay, so here I've just drawn the lines. So if I can cut this into 4 9 by 9 multipliers, I actually have to change a few of these boundary cells to basically have a slightly more complicated logic function. But if I do that, I actually have 4 9 by 9 multipliers. So that seems pretty good. Now, is that useful? Well, 9-bit data is actually common in some applications too. So for signal processing for things like wireless base stations, you usually have to do it in 18 bits to get enough accuracy for the data coming off the antennas. But if you're doing video processing, you usually have 8-bit pixels. If you're doing machine learning, you can commonly do things in 8 bits. CNNs, like their input is video and they're tolerant of low precision. 8 bits makes sense. So 9 bits like an extra bit of precision, kind of get a bonus, right? So it seems good, could be useful. Okay, the thing that you have to think about though is that if I built this, I actually need four sets of inputs. Each of them is 9-bit, and I need 2, right? So to do 9-bit multiplication, I need 2 9-bit inputs. And if I'm going to do 4 of these, I need to do that 4 times. If I multiply all that out, that's actually twice as many input ports as I needed for my 18 by 18 multiplier. And if I do the same thing for the outputs, I'm going to find that I have twice as many outputs as well. So for this reason, what you'll usually find is a lot of FPGAs will support, dividing their multipliers up into smaller pieces. And they could naturally get, in this case, for example, 4 times as many 9 by 9 multipliers. But usually what they actually give you is only half as many, okay? And it's because they're limited by the inputs and the outputs. I don't want to add all the routing ports that I would need. So I could add more routing ports, but if I thought the most important mode was 18 by 18, I should add just enough routing ports for it, and everybody else lives with it. So, so generally you'll find this would be instead be 2 9 by 9s. Okay. So early FPGAs, yeah, for many generations FPGAs had, well, no multipliers, then they had multipliers. And then they started adding more circuitry around the multipliers to make more powerful DSP blocks. So a common set of multiplication is to make FIR filters more powerful. So FIR filters are one-dimensional convolution. It's used a lot in signal processing like wireless communications. So it's a one-dimensional convolution on a stream of values. And a lot of filters are symmetric. So symmetric means like if I have n coefficients, coefficient 1 and coefficient n minus 1 are the same, okay? You don't have to do it that way, but a lot of filters do it that way. It has some nice properties. And if your filters are symmetric, you can basically regroup things so that you wind up with half as many multiplications. You basically add pairs of samples and then you multiply. So you can cut your multiplications in half, and multiplication is more complicated in circuitry than addition, so that's a useful thing. So this is actually this is like a FIR filter, okay? It's a FIR filter that's implemented in what's called a systolic style. So systolic means that the data is moving kind of forward 1 beat at a time, and the outputs are coming out 1 beat at a time, so it's a very efficient form of streaming hardware. Don't worry if you can't like absorb all this right away. Not really expecting you to kind of go, okay, I got the whole FIR filter structure. But basically, we've got coefficients multiplying input data, and the input data is getting delayed. This is a symmetric filter, so we're adding together sort of the first piece of data and the most recent piece of data and multiplying it, and then adding together all the partial outputs to get our Y. This structure basically has lots of local short connections, and it's deeply pipelined, so it's fast. And what's shown here in sort of outlined is what Stratix 4, which I'm going to show some area results on in a second, hardens in the DSP block. So it's got a multiply, it's got an add, it's got pipeline input registers, pipeline register, output register. It has dedicated interconnect, so this is actually made with special wiring that goes right to the next block. So this is very efficient, right? Doesn't use very much wiring and is deeply pipelined. So that's what Stratix 4 does. The next generation from both Altera and Xilinx basically went further and found that, I think Xilinx did this before Altera, but eventually both of them put this in. Basically, the DSP blocks in the most recent devices you'll find capture all of this. So capture the multiply, capture the accumulate, capture all these pipeline registers, the dedicated interconnect, and they also have these pre-adders. So for symmetric filters, this addition can also get sucked into the DSP block. If you write, in HDL a bunch of multiplies and adds, it's very unlikely the CAD tool is ever going to find all this. This is where you instantiate the DSP block and you say, I want exactly this. The multiply is more expensive than most of the other hardware. So while this is a kind of a reasonable amount of other stuff, it's trying to basically make the most out of the multiplier and make a really common use case for FPGAs really efficient. So you wouldn't do this unless you had a lot of FIR filter structures and structures like this. But there are enough that this whole block is basically hardened in the most recent FPGAs. Okay, so the reason I showed you that was this is another example of where we can actually take the areas of soft versus hard implementation. And this is again from the Principles and Practices paper, so you may have already seen this. Okay, so if we take a, let's start down here. Okay, so this is a FIR filter where all the coefficients are different. And we could build it with the DSP blocks, okay? And it takes a certain amount of DSP blocks, and for this chip we know the area, so it takes 1 unit of area, and it clocks at 510 megahertz. If we put it in the soft logic instead, it takes 3.9 times as much area, and it clocks at about half the frequency. Okay, so hardening was a pretty big gain, and that's if we know the coefficients in advance, and we'll never change them. So in that case, the synthesis tool can basically optimize the logic more because it knows all the filter coefficients. If we don't know the filter coefficients, or they're going to change, then the gap's even bigger. It's 8.5x, and the frequency we get is only 0.4. So this gives an idea of like what gains do we get from hardening. And yeah, that's probably the part of this table that I kind of want to go through. So does that make sense? So bigger gains when we know less, right? When we have to make our system take arbitrary coefficients, which is pretty common actually. You might want to change these coefficients at runtime. Then the overall gain of hardening this was about 8.5x in area. Still quite a bit less than remember we had the Rose and we had the paper earlier on. There's a Rose and Kwan paper that looked at what's the gain of hardening FPGA logic. We're not getting the 30x or 40x that they were talking about. And the basic reason is when we build this DSP block, we still have to build some configurability into it, right? So there are going to be some registers in here, some paths in here, some configurations here that we're not using. So even when we're trying to use it to its absolute maximum capability, we're not going to get to those 30 or 40x density gains. It also still has to connect to the program we're routing, and that also is going to limit our gains. So we get a good gain, but we're not going to get to those 30 or 40x. This is again from that Principles in Practice book or paper, but it basically shows the evolution of DSP blocks, right? We went from multipliers. So in the first multipliers in FPGAs are hardened multipliers where Xilinx did them for 18 by 18. Then Altera basically made a more flexible DSP block where you could kind of break it into smaller multipliers or combine it into bigger ones. Then gradually we added more things around the multiplier, like Xilinx added ALUs and pre-adders. Intel put in floating point, and we gradually got more and more fracturable modes, so more different precisions. So Versal supports 1, 2, 3, 4, 5 different precisions, and that's continued. And then one that I'll talk a bit more about is this Stratix 10NX from Altera. And it basically has a lot of multipliers. Okay, so you notice all these ones are kind of, one big multiplier or maybe 2 or 4 smaller multipliers. This one is like 30 to 60 small multipliers or 1 big multiplier. Okay, so it has a lot more small multipliers than the other ones. Okay, so one trend is more fracturable over time, more things around the multiplier. So multiply, accumulate, and then FIR filters, and then dot product circuitry and floating point. And yeah, this last one I'm going to talk some more about. How do you get so many small multiplies? Yeah?
For these Stratix in 2002, I noticed that their 36 by 36 gets fractured into 4 18 by 18. So that would be the case where the inputs and outputs are double the number of ports, right?
Yeah, what actually happened here is what the main mode is really the 18 by 18. Okay, so that's why it's not, I think the red is what was added. So it was really built for 18 by 18 because that's the dominant mode, okay, that was most used. So you could fracture it down to 8 9 by 9s. You could also take 4 18 by 18s and combine them to make 1 36 by 36. And that uses actually fewer routing ports, so that's fine. And that's kind of the opposite of fracturability. It was like composing them. But it was really built to make sure that one worked well. Does that make sense? Okay, so let's see, maybe I'll finish off this. I'm going to finish off this last DSP block and we'll be done for today. Okay, so I'm going to talk about this one. So there's been this gradual evolution where the DSP blocks have gotten more flexible, more powerful. And this one's kind of a interesting jump. Yeah,
It seems familiar. We did a rating on this already, I think, right?
yeah, yeah. So this looks familiar, it should, okay? This is me highlighting things that maybe you already know. So if you memorized it all, you're like, I could get up there and do it. Okay, so let me talk a little more about this one though, because it's a little different. Okay, so that is this Stratix 10 NX tensor block, and this got carried forward to the next generation. So Xilinx's Agilex. So sorry, Intel's Agilex. Xilinx doesn't have Agilex. Okay, so the most recent Altera FPGAs have this thing called a tensor block. So what is it? It can do a lot of small multiplies. So it can do 30 int8 multiplies, or instead of two 18 by 18. So you can't fracture an 18 by 18 multiply into 30 int8s. So this means Altera has built, two int8 multiplies, and then they built a whole bunch of int8s, right? So they paid the extra hardware cost to build that. And they can actually fracture these down further. So they can actually do 60 int4. Okay, now int8 multipliers aren't that big. So it does cost you something to build 30 of them, but clearly it's acceptable. And int4 is even smaller. They probably split the int8s into two, just like the way I showed you. But let's just take a look at the inputs and outputs. Okay, so the regular Altera DSP block, before they did this, had 96 inputs. It was enough to basically feed two 18 by 18 multiplies plus some other circuitry. And they had 72 outputs, okay? And that was enough for two 18 by 18s. But if we actually want to do 38 int8s, okay, so we need 2 times 8 times 30, that's 480 inputs. And then our output width is going to be 16 bits, so we need 16 times 30, which is, again, 480. That's like a lot more than 96 and 72. So this block is looking, even if you can make these int8 multipliers pretty small, this is looking pretty expensive. So what they did is basically the tensor block is an exercise in, well, how do we get rid of those input and output ports, but still make something that is useful? So the first thing they did is they said, well, we're not really targeting this to have 30 independent 8 by 8 multiplies. This is really going in to do things like convolution and deep learning, which can be phrased not just as multiply accumulates, but as dot products. Okay, so we go up one level, what we're trying to do are dot products. So in dot products, we're going to add the outputs together. So they take groups of 10 multiplies and say, we're going to add all those 10 together, which means instead of having 30 outputs, we now only have 3 because we have 10 element dot products. So now we're down to 72 outputs. If we didn't want to do dot products, this was a really bad idea, okay? But if we mostly want to do dot products, this was a good idea. So that's the first thing they did. They also built the ability to accumulate larger dot products by basically having dedicated routing that basically feeds into these adders. So that means that the dot product up here, this 10 elements, can add into these 10 elements. And I can basically construct larger dot products, like 20 by 20, 30 by 30, et cetera, without using the regular programmable routing. I can use these dedicated ones, which just reduces burden on my programmable routing and ensures I can run at a high clock frequency because these are dedicated routes with registers on them. So that looks pretty good on the output side. I still got a lot of inputs, though. So what they did next is they said, okay, well, I don't need, maybe I can get rid of some of those inputs too. So the first thing they did is they said, I'm going to broadcast one set of inputs to all 3 .10 engines. Okay, so that's a restriction. Instead of having 3 10-element dot products where I can do anything I want, they're saying I have to share one of the vectors. Okay, so the first vector is going to all 3 dot product units. So it's an additional restriction. If I needed 3 independent completely independent dot products, this doesn't work well. But this gets rid of a bunch of inputs, okay? Because I bring one vector in once and use it 3 times. The other vector I'm still bringing in 3 times. And then the last thing they did is they said, okay, so one of the inputs is being broadcast. The other one, I'm going to actually store locally in registers. And I'm going to build basically 2 chains of registers. And I'm going to build, I can basically bring in data from either the regular programmable routing or the block above me. And I can shift it in over several clock cycles into these registers while I'm computing off the other ones. Okay? So they can basically hide the latency to load the other 3 vectors while they're doing computation with something else. This is useful if, basically, if I can use this, what I load into these registers for several cycles, right? So I want these vectors to be multiplied by several things that I bring in on my other input. Then I can basically be doing that while loading the next set of vectors. And that, you have to be careful about that, right? Like if you can't handle that, then this block's not going to work well. But after making that change, they get 80 inputs. And now this is basically down to what the regular DSP block had. So it turns out they could fit it essentially into the same footprint. So they had to remove a few modes from the DSP, but after that, they said, okay, we can now make this the same area. What they get now is 15 times the int8 operations in this, essentially the same area as one of their DSP blocks, but they have significant I/O constraints. How well does this work? Well, so basically you saw in an earlier lecture 2 of the designs from my group that actually used this block. So to use this block, you actually have to restructure how your computation is done and how you use the interconnect. So you can't just take your RTL and recompile it and say, you should take all my multiplies and just turn them into dot products with all sorts of preloading and stuff. Like there's no synthesis tool that is going to do that. So to use it, you do have to do a significant amount of structuring of your algorithm so that everything can be arranged this way. But we did that for HPipe, which if you remember is a CNN accelerator, and it uses a data flow style. So you have all these operators and you're streaming data from one to the next. And what we did is we preloaded the activations and we broadcast the weights. So there's basically 2 ways of reducing the input usage. Preload something into those registers and use it for a while, and broadcast one of the vectors. So we use both those techniques, and we got a 5x speed up over basically a comparable Altera FPGA without these blocks. So it did work quite well. It's not the 15x peak, because there's all sorts of other stuff that can become a bottleneck, but it's a pretty good speed up, given that the chip is about the same area. One of the things that we did in HPipe is it has clever circuitry to essentially skip over 0 weights. So there's a bunch of papers that show that you can make CNN sparse. You can remove a lot of the weights and replace them by 0. And if you're careful in your training, you don't lose accuracy. And one of the things HPipe can do is it actually uses the FPGA muxing to just skip over those, so it gets faster. Unfortunately, that is hard to do when you have to organize the data so much into vectors and reuse it. So some of the cleverness that we could do in the algorithm before, we couldn't really do with this block. So if we had a sparse CNN, we basically couldn't use the tensor blocks as well. We got a 1.9x speed up. So we also did the same thing for the NPU. So that was this overlay style. So overlay, again, is like a really unusual form of soft processor. And the NPU, again, could, with one instruction, launch 45,000 in operations. And it was targeted at basically a bunch of other neural networks, so MLPs and graph neural networks and so on. And in this case, we again preloaded the activations. And we had to, if you remember the deep learning part lecture, one of the things FPGAs are good at is low latency. They don't need batching as much as GPUs. But to get the most out of these tensor blocks, we had to do a little bit of batching. We had to basically say we have 3 inputs, and we want to solve those 3 together. That was necessary for us to essentially make use of that broadcast feature. With that, we got a 3.5x speed up. So you could get a bunch of gain out of this. So anyway, so the interesting thing about this tensor block is it is it's more special purpose. You have to organize your computation thinking about it. If you do that, you can get a lot out of it, but there are some trade-offs. Okay, and I think that's where I'm going to end for today. So yeah, we're done for today unless there are any questions. And that's still on, it's not on daylight savings, so I'm not an hour overtime.
Are you kidding? I was gonna say 9 p.m. Bob, are you kidding?
Yeah. Okay, we're done for today. With that, I think that means I've gone long enough.